Welcome everyone to the 5th Acceleration AI workshop. I am Yassine Hariri, your host for this annual event. And as a senior AI ML scientist at CMC Microsystems, I am honored to unite industry and academic experts to discuss the latest trends in AI hardware, software, and application, both in the cloud and at the edge. I extend my gratitude to our esteemed speakers for graciously accepting our invitation, and a big thanks to all attendees. The workshop this year focused on AI acceleration, highlighting edge AI evolution alongside emerging megatrends such as generative AI hardware advancements, and software innovations. Our aim is to exchange insights, foster collaboration, and bridge the gap between industry leaders and AI researchers and startups. So whether you are professor, researcher, or industry professional, your active participation is vital in propelling innovation forward. Before we start, please be advised that this event is recorded and the recording will soon be available on CMC YouTube channel. So today's agenda showcases a convergence of industry luminaries and academic leaders collectively shedding light on the forefronts of AI innovation. Our program begins with a brief presentation from CMC Microsystems, delivering opening remarks to set the stage for the workshop. Following that, we will explore generative AI on the edge with Pierre Paulin of Synopsys. And next, Tom Stesco from Tenstorrent is presenting an open ecosystem for accelerating AI compute. Jonathan Dursi from Nvidia reveals strategies for tackling complex AI workloads with the GH200 Grace Hopper Superchip. Then we will navigate through Flo Wohlrab's presentation on industrial-grade open-source RISC-V CPU IP. Then we will have a 10-minute break, and after the break, Bill Jenkins of Untether AI will shed light on energy-efficient AI inference accelerations. Next, we will join Stephen Su from ARM, who will unveil the transformative potential of ARM Helium technology for edge AI, followed by Hajar Abedi, a researcher and postdoc at the University of Waterloo, who will present insights into next-generation AI resident activity monitoring. Professor Andreas Moshovos from University of Toronto follows with a deep dive into software, hardware assists for training and inference. Then last but not least, Professor Warren Gross from McGill University unravels the hardware intricacies behind stochastic simulated annealing for large-scale combinatorial optimization problems. The day conclude with an open discussion, providing an interactive platform for collaboration engagements. So a brief intro of CMC Microsystems. We are founded in 1984, and we are not-for-profit organization committed to accelerating research and innovation in advanced technologies. Our goal is to reduce barriers to technology adoption by sharing platform technologies and providing access to state-of-the-art manufacturing and testing capabilities from microelectronics to quantum technologies. We offer services aimed at simplifying access and reducing costs for researchers and innovators. Our autonomy from particular applications ensure our services are equally beneficial to those involved in advanced manufacturing, clean tech, agriculture, health, and beyond. We provide essential infrastructure and strive to diminish obstacles to embracing state-of-the-art technologies, enabling the Canadian ecosystem to pursue research and development with enhanced ease and efficiency. We are honored to contribute to a Canada-wide partnership encompassing 68 universities and colleges, facilitating the connection of 10,000 academic participants with over 1,000 companies to develop, produce, and test micro-nanosystems prototype. This collaboration fuels innovation and empower HQP, enhancing skills and opportunities. We provide our products and services under 3 banners: CAD, Fab, and Lab. CAD consists of state-of-the-art software for successful design. Fab consists of simplifying access and reducing cost for working prototype, and Lab consists of tools for test and demonstration. This slide summarizes a fabric. It is a pioneering over $200 million initiatives, which consists of the development of Canada's first ever national ecosystem dedicated to addressing the crucial need for semiconductor capability. This innovative project includes 5 key activities: create semiconductor device fabrication capacity, accelerate IoT products and services R&D for SMEs, develop essential skills in HQP for industry, advance quantum technologies to market, and foster growth of Canada's semiconductor ecosystem. So I'll give a brief summary of CMC Microsystems support for Edge AI solution. We are considered as a one-stop shop for Edge AI development from concept to prototype, so including conceptualization, data management, model training, model optimization, inference, and deployment. We offer these products and services by supporting an advanced infrastructure that enable our users to effortlessly train, optimize, and deploy ML models on edge devices. On the cloud, we offer access to advanced cluster for training large neural network on custom accelerators, GPUs, FPGAs, and CPUs. We support a wide range of software frameworks for machine learning training and inference. And with the collaboration with our partners, Untether AI and Tenstorrent, that are presenting today, we offer advanced hardware for AI inference at very low power. These are custom AI chips specifically designed to support the next generation AI workloads. We are also part of a large ecosystems in Canada supporting RISC-V, partnering with OpenHW Group, who are speaking today in the workshop. And we will hear more from them on the latest news about these IPs and RISC-V cores. Join the discussion. This is a LinkedIn discussion group that CMC is maintaining to get the latest news about CMC AI initiatives, as well as connecting with startups and researchers in the Canadian ecosystem. Now, let's dive into the main topic today, the workshop, Accelerating AI 2024. So Accelerating AI 2024 focuses on the challenges and opportunities in cloud and edge computing. Our goal here is to unite industry and academia to share trends, identify challenges, explore collaboration, and pinpoint common infrastructure requirements to support academia and startups in the Canadian ecosystem. So as outlined in the workshop agenda, the Acceleration AI 2024 presentations delve into cutting-edge topics that are shaping the future of AI. Our sessions cover a wide spectrum of crucial areas ranging from generative AI on the edge to energy-efficient AI inference acceleration. We will explore the latest advancements in AI compute ecosystems, discuss industrial-grade RISC-V CPU IP, and delve into next-generation AI activity monitoring, as well as machine learning acceleration for training and inference. So this slide summarizes the important macro scan on the edge AI. So the most important mega trend is the emergence of multimodal generative AI, which has a massive economic impact. In fact, generative AI is poised to automate 60% to 70% of the work, and 60% favor multimodal AI by 2026, a rise from 1% in 2023. Bigger LLMs, diminishing returns, so the mainstream research and development optimize large language model instead of enlarging them, although we will see bigger LLMs in the future. Edge AI transformation. This is another mega trend which consists of the migrations of AI workloads from the cloud to the edge because of the advantages that you're already aware of, including low latency, bandwidth saving, prioritize data, privacy, security, and autonomy. This has led to a critical need for energy-centric edge AI hardware that deal with this increasing complexity. Since 90% of the power is consumed by data movement, we have noticed the emergence of innovative AI hardware that deal with this main issue. At memory, special architecture for low power scalability is one of the emerging trends in AI hardware. Domain-specific neural processor, complex memory hierarchy, and massive parallelism, without forgetting efficient ML mapping tools that deal with the increasing software complexity in AI workloads. We also noticed the exploration of non-conventional architectures that are based on quantum, spiking neural network, and analog computing. Now let's dive into the workshop agenda. First of all, some housekeeping. I request presenters to keep their presentation time to 15 minutes, allowing 5 minutes Q&A. So when you see me appearing in your screen, this means that you have 2 minutes left to conclude your presentation. So I have, because we have a high number of speakers, we will make sure that we respect the time allocated to each presentation. So let's kick off this workshop with Pierre Paulin, Senior Director of R&D, Synopsys, bringing over 25 years of experience in embedded systems technologies. Pierre's expertise will illuminate generative AI on the edge, exploring its transformative application across various sectors. So I will unshare my screen, and I will allow Pierre to share his screen and start his presentation.
Thank you, Yassine.
Stage is yours, Pierre.
Audio check. Can you hear me, Yassine?
Yes.
Great. Slides are visible?
Yes.
Excellent. Thank you for that excellent introduction. You've introduced all the key concepts, and I'll be covering those, of course. So I'm Pierre Paulin. I'm responsible for the system architecture team at Synopsys, working on neural processing units. And I'll be talking about underlying technologies and trends for generative AI applied to edge applications. So quick introduction of generative AI. I think no one needs any introduction anymore, but a reminder of some of the key recent achievements. And then diving in on some of the technology behind generative AI, and that's the rise of transformers, moving from what I'll call classic CNN, which is only 10 years old, but in the last 3 or 4 years to transformer-based solutions, and which are the kind of the backbone of generative AI. What are some of the features and challenges of supporting transformers, why they're here to stay, and how do we support transformers and Gen AI, which builds on top of these, on our NPX6 neural processing unit. So generative AI is built on top of transformers, and some well-known examples, of course, ChatGPT and Llama, that everyone's familiar with. Text-to-image models, Stable Diffusion, DALL-E, Midjourney, and I have a small example here, which my boss loves because he's German, and he confirmed that this is an old-fashioned German typewriter. And of course, the cute dog always gets attention. And we've seen these on high-end GPUs, and the trend in the last year is we're seeing some of this Gen AI moving to the edge. And examples are GPT-J moving to the MLPerf Edge benchmarks as one evidence of that in last September. And again, transformers are the building blocks of Gen AI, and so I'm going to be focusing part of the talk on transformers. So before transformers, there's been a decade of CNN development. In fact, there's been 30 years of neural network development, but really, with the University of Toronto pioneering work back in 2012 and AlexNet, that was really the beginning of kind of mainstream CNN. And those of you who have been tracking this for the last 10 years, many of these are familiar to you. And all that led to, starting from, kind of 60% accuracy to a kind of a peak for CNN, about 90% accuracy for the ImageNet benchmarks back in 2021. And very quickly, transformers, which were in fact designed for natural language processing, were reapplied with very small changes for vision applications. And if we ran those same benchmarks in 2022, 1 year later, they already surpassed the best CNNs and a decade of work in about a year. Transformer-based vision applications were seen to surpass CNNs in accuracy. So this is maybe a reminder of I'll call a classic is the archaeology now, but that's not so long ago. We were all working on SIFT and other classic computer vision, algorithm-based approaches, which peaked at about 50% accuracy. Then the big jump with AlexNet, VGG, ResNet, and so on, all the way up to kind of the peak of CNN-based solutions with systems like EfficientNet. Then in green, we see transformers appearing, VIT, CoatNet, and kind of in 23 at least, the leader was a fine-tuned COCA. So state-of-the-art accuracy for vision, which is not even designed for vision, pretty much out of the box within 1 year. And key thing is inside of these networks, we use attention-based modules, which are better at recognizing more complex objects, and I'll talk more about that. And we're seeing that emerging and very recent NPUs have been optimized specifically for high-performance execution of transformers, and the Synopsys NPX6 is an example of those. So, of course, transformers have a cost. So if we take our kind of relatively state-of-the-art CNN-based, well-known MobileNet V2 for small image size, we're at about 70% accuracy. If we take that as a reference in GOPS as 1x, we're getting about 32x frames per second relative to a vision transformer. A vision transformer, on the other hand, is closer to 84% accuracy, so a significant leap in accuracy. The GOPS is 58 times higher, so it does come at a cost. But the relative frame per second is not 58 times lower. On the other hand, it's 32 times lower. Because as it turns out, vision transformer mapped more efficiently to an NPU, or at least the NPUs we've worked with, than the old CNN-based MobileNet V2, which use depth-wise separable convolutions, which are harder to get high resource utilization. So it's 58 times more DOPS, but only 32 times less performance. That being said, that's still a major gap. The other, of course, cost of transformers is that the models are huge, and that's true for CNN and transformers. To achieve these state-of-the-art results, 2 gigaparameters is common. And this, as such, is great to win a best ImageNet award, but not practical for embedded. But that was a few years ago. Already, we're seeing innovations in developing new, more compact transformer-based vision classifiers. So there's a paper by Apple 2 years ago that developed a mobile VIT. So it's a small transformer, also combines both transformer and convolutions. And if you look at the range of MobileNet V1 to V2, V3, and ShuffleNet, all of those are kind of in a constellation that are pretty close to each other, that the accuracy goes down with model size. And then you see at the top this red curve, which is in a category of its own, which is typically 5% higher for the same model size. And so you'll see here, and specifically for this result, MobileNet V2 with 2.6 million parameters has a 70% accuracy, while MobileNet VIT from Apple, ours is Apple, I took this from the paper, has a 5% accuracy increase, which is huge in this space. Looking at more closely at those results in the paper, MobileNet V2 in this specific comparison is 3.5 million parameters. The mobile VIT is actually smaller, so it's a 0.7x relative to the original MobileNet V2. The number of flops is 2.3x, so there's a significant increase, not 5x or 50x as we saw before, but 2.3x. And there is a good, in this space again, 1.5% accuracy is hard to achieve, so that's a good accuracy increase. Now let's look at the actual results. So if we run this MobileNet V2 on a CPU, not on a neural network processor, but on a traditional CPU inside the iPhone 12, the latency is 7.5 milliseconds. So on a kind of mostly sequential CPU, the time is 2.4x higher at 18 milliseconds roughly, which is logical because it's 2.3x more flops. So, the ratio is about the same. Now, what is more interesting is if I look at the MobileNet V2 and we take that 7.5 millisecond, we map the same algorithm onto a dedicated neural network engine, the NNE, which is part of the iPhone 12, we see an 8x increase or reduction in latency, 8x increase in performance. Now, interestingly, when you take mobile VIT and map it onto that same NNE, you're not getting the 8x improvement. You're only getting 2.5x. And so the observations from the authors at Apple, is that the mobile VIT is slower than CNN-based, and the accelerator on the iPhone is really not optimized for transformers, and it really was optimized for CNN, and therefore that explains the 8x versus 2.5x improvement. And the authors speculate that future AI accelerators will better support transformers. And that is exactly what happened even since in the last 2 years, and I presume at Apple as well. So what are the features and challenges? So clearly, transformers were developed, and they're the basis for natural language processing, and they're the basis for applications like ChatGPT. And what is really interesting is that they lead the state-of-the-art results in other application domains like vision and speech. And that was done with surprisingly little modifications, as I shown earlier. And models that combine the best of both worlds of attention and traditional convolutions are outperforming conventional neural networks on vision tasks, even for small models. So we're already seeing the models getting more efficient and starting to outperform for similar model size. We strongly believe that transformers are not a temporary glitch and a fad. Both Gen AI and the transformers, beneath them are there to stay, and there's fundamental reasons for that, which I'll talk about in the talk. So intuitively, and of course in 15 minutes, it's going to be very high level. Let's look at some of the differences between convolutions versus attention. First key thing, of course, convolutions based on 3x3 convolutions around the red pixel in the center. That is fixed. It's hard coded. It's part of your CNN algorithm. You are reading the 9 pixels around the center pixel. Attention does not have a fixed spatial location. Really, the attention in transformers is based on learned attention, and that is based on the application. So you have a much more flexible access to the surrounding pixels, and that is much more context dependent and knows much more about the world that it was trained for than convolutions, which are kind of hard-coded as a 3x3. So that's a first intuitive, visible difference between those two. And what does that mean? Well, convolutions are good at recognizing very regular things. It could be an example is cat fur, very standard, easy to detect patterns. Of course, you can detect cats and so on in regular situations, and they're very good at that. What really distinguishes, transformers and the attention mechanism is that transformers are good at looking at more complex patterns. And here we have, hard to recognize cats in unusual situations, either a fat cat, a cat with his head in the toilet, and so on. And that is a direct consequence of this more flexible use of attention, which looks at the more relevant pixels and not just the 3 nearest pixels, the 9 nearest pixels. So what is the structure of a transformer? Well, you have the classic graph here. Zooming in, basically you have each token. In this case, the tokens are words in the traditional initial use of transformers for natural language, and you do correlations between different words. Is this the real life? And there's a strong correlation with other words in that sentence. The application of transformers for vision really uses the same approach. It's except that instead of tokens, which are words, remarkably, this works very well with tokens that are just patches of images. And those patches, of course, have correlation with other patches in the image. And the same approach can be used. But why do we think attention and transformers are here to stay? Let's take a simple example. panoptic segmentation is kind of the state of the art of the the most complex CNN-based solution. And if you take this odd image of a guy ironing on the back of a minivan, the panoptic segmentation will recognize, well, there are two cars, the yellow one, taxi one, and the yellow minivan, and will give different colors to those cars. It recognizes that there are different instances of cars. And it also detects all the pixels of the cars, where the cars are actually located. That's the segmentation part. And of course, it recognizes a person, and it's the same semantic segmentation, and so on. But that's it. That's pretty much a very shallow and kind of superficial interpretation. And that's useful, of course, in autonomous driving, but it's not sufficient. Let's take that same example and say, what is unusual about this image, and ask Lava. The unusual aspect of this image is a man is ironing clothes on the back of a yellow minivan while it is on the road. This is an unconventional and unsafe place to perform such an activity, as ironing clothes typically requires a stable surface and appropriate equipment. Ironing clothes in a moving vehicle could lead to potential hazards for both the person doing the ironing and other road users. Now, first conclusion, clearly lawyers contributed to some of the training here, but jokes aside, this is a remarkable and deep interpretation. And if you have an autonomous car, do you want to interpret it this way, or do you want to interpret it that this is actually an odd situation that is probably dangerous, and you probably want to steer clear of this minivan carrying a guy ironing? Well, that's just a contrast. Of course, it's not just one or the other. It really, our experience and what we're seeing in the state of the art is that there are really good things about CNN, and there are other good things about, of course, about the new Gen AI and transformers. And you need to balance these strengths in order to get efficient, compact implementations that use CNNs where they're efficient and they're compact and map nicely, and use these new larger models where you need them. So with the few minutes I have left, just want to introduce our NPU, a neural processing unit, which is called the NPX6. It's a scalable architecture. It has multi-cores. Each core has 4096 max, plus a generic tensor accelerator. You can scale that to about up to 24 cores. That will give you up to 440 tops, our highest benchmark. And you can also instantiate multiple NPUs too. And we have customers using over 1,000 tops in the automotive space, for example. We, of course, have tools with that. There's two main building blocks, the convolution accelerator, which, of course, supports CNN, but also supports the most modern network structures, including transformers. And then anything that is not a convolution and matrix multiplication runs on a more general unit called the generic tensor accelerator. And that's a very flexible unit that supports de facto standards like TOSA, tensor operator set. As Yassine mentioned, memory hierarchy is absolutely key. DMA broadcast, multicast, multi-level memory is all critical pieces, and really we've been doing this for about 11 years now, and that's really where most of the R&D has gone, both on the tools and the movement of data. So how do we support transformers? Well, there's some key features. So the convolution accelerator needs to support matrix multiplications, not just vector matrix, and features like feature maps on both operands need to be supported as well. Our generic tensor programmable unit needs to support softmax across channels and feature maps. Key functions like L2 normalization are supported, and many transformers use this GELU activation. There are new ones appearing, but this is programmable in our engine. That's just one example. And then finally, the inside each core, you have a complex L1 DMA, which needs to do things like reading multiple vectors based on a vector of addresses that are computed, dynamically by the tensor accelerator. Again, I'm going real fast just to give you a sense of some of the features that are needed for efficient support. So remember the Apple example where we had the iPhone 12. What's not there in the paper, but if you reverse engineer the results, the Mac utilization for a transformer is below 1%. So clearly the CNN-based engine used in the old iPhone 12 is not at all efficient for transformers. And so this is just, these are our kind of recent benchmark results for VIT and SWIN, showing that we're not anywhere close to this 1% range, but we're easily in the mid-60s and sometimes up to 70%, depending on the image size and conditions and bandwidth. And all this for reasonable bandwidth numbers, as you can see. So let's go from transformers. Gen AI uses transformers, and I'll finish with these slides just to say that we're able to map these stable diffusion. This is a very natural mapping for us. There's no bandwidth or resource bottleneck. And we're already comparing with the kind of the high-end GPUs and the Tom's hardware benchmarks that looks at things like the RTX 4080, which is a high-end Nvidia GPU. We're getting results that are already similar to those with this machine. And Gen AI, Llama 2 is a well-known example. So this also maps directly onto our machine. And now the challenge with these large models for any machine, not just ours, is bandwidth. And the performance is completely and at least is dominated by external DRAM memory bandwidth. So most support for this uses integer 4 for coefficients to improve the use of external bandwidth, and internally use integer 16 for feature maps to preserve accuracy. And we've benchmarked this, and there are some public domain results from some leaders in this space. And not surprisingly, because it is bandwidth dominated, we're getting within 0.1% the same result. So we're confident we're using the bandwidth that's available and getting world-class results. So first results look quite encouraging. I'm out of time, so I'll just summarize. And transformers, are a deep learning model that was initially designed for natural language processing. We're already shown that they can lead to state-of-the-art results for other application domains like vision and speech. We designed the NPU with transformers as a key driver. We started the design about 3 years ago and introduced it last year. And we've shown that as you've seen our results with VIT and SWIN, we're getting 65% plus macularization. And the outlook is Gen AI builds on top of transformers. So that's a really strong basis. And we've seen examples like Stable Diffusion and Llama. Those are moving quickly in the embedded space. And as your statistic, Yassine, was a couple of percent of our customers were asking for this a year ago. And unusual places, 70% of our customers, including spaces we never expected, are now asking us for benchmarks. So this is clearly moving into the mainstream, and we're working hard to get this to our customers. Thank you. I'll have time for, I hope, a few questions.
Great. Thank you very much, Pierre, for this great presentation addressing the unique challenges of generative AI on edge devices. I will encourage the attendees to either ask questions on the chat or unmute yourself and ask the presenters questions directly. We would like this workshop to be as interactive as possible. Maybe one question, Pierre, is how does your approach on mapping Gen AI application on edge devices deal with the real-time requirement of some applications?
Well, in the end, it's about, we have a configurable machine. So the first element is for a stable diffusion in that class is really, we have a good mapping in terms of resource utilization. So basically at 65%, we of course can go a little bit higher in theory. It gets harder and harder. So basically you're just configuring the machine to meet your real-time requirement. And since we can go from 1 TOPS to 1,000 TOPS, the customers can pick the right configuration and meet their targets. Usually it's less about the machine size and it's more about bandwidth, and the effective use of bandwidth is the biggest challenge.
Great. Any questions from the attendees? Please unmute yourself and ask questions.
Are my devices available for university? Well, that's a good question for Yassine, and Yassine will call me right after the meeting, I'm sure. We haven't done that yet. This product is only a year old, so first steps first. We've licensed it to some major mainstream customers, so our focus is there for the moment, of course, on the business side. But of course, this makes perfect sense. We believe we have a world-class machine, and it makes perfect sense to discuss this next step. And I'd be happy to talk to Yassine about this in the near future. We've done that in the past with CMC in my former life, as you know, Yassine, with other companies. So, and we have also cooperated with our current, previous generation as well. So, we're happy to entertain this.
Great. One last chance for questions. Okay. Due time limitation, we will move to our next speaker. Thank you very much, Pierre, for accommodating this presentation in your busy schedule. I know the time changed, so
no, but I'm gonna hang around till 11 p.m. my time for the open discussion at the end, and I'm really interested in listening to the other speakers. So I'm going to be around for most of the evening and most of the afternoon for you.
Perfect. Thank you very much. Let's now move to our next speaker. Tom, you can share your screen. So we have Tom Stesco, staff field application engineer at Tenstorrent, delving into Tenstorrent's open ecosystem for accelerating AI compute. Tom's insights promise to revolutionize the AI ML software development and AI hardware for inference. Tom, the stage is yours.
Can everyone see the slides and hear me okay?
Yes.
Awesome. Yeah, thank you. Thanks to CMC and thanks Yassine for hosting the workshop. So I'll try to get through all this material pretty quick, make up for some lost time. Okay, let's get started. So Tenstorrent is a engineering design company. We're building the next generation computers. We're calling them graph computers. And we believe very heavily in open standards and open source, which is why we're using RISC-V at the core for all of our hardware. So we have AI accelerators, high-performance RISC-V CPUs, and ML and CPU chiplets. So that's kind of the pieces I'll be touching on today. So what is a graph computer? So as Pierre mentioned, we're looking at transformers as really a paradigm shift in computing and not an accidental architecture. But you can kind of think of the old way we think of computing with this 10,000 or 10 million line C program with a sequential narrative and control flow. Now we're looking at a compute graph as a directed acyclic graph. You can see on the left here, transformer encoder-decoder architecture. And each layer of that network is kind of like a coarse grain operation. We want to map that faithfully onto novel hardware. So you can kind of see this cartoon mapping of this network onto a bunch of cores. You can kind of see they're overlaid over the real cores. And that's kind of our idea of our data flow architecture or near memory compute, spatial compute as well. There's a lot of names for this, a lot of terminology to be figured out to be sure. So you can also see on the far right more detailed idea of this. Also here, I'm going to call out we not only have the AI accelerator cores, but CPU cores. So we're integrating those as well into the same package. And that's going to allow us to have specific control flow and conditionality. The other key piece is the interconnect. So I/O is another key theme that we're going to be touching on. Okay, so what's in our 10.6 core? That's our current generation here, Grayskull. That's generally available today. So this is a grid of 120 10.6 cores in the same chip, same package. On a board, you'll also have PCIe and LPDDR4. So then inside that core, we have 5 baby RISC-V processors, and those really facilitate the control flow and data movement. So there's 2 router edges on a network on chip or NOC, and the RISC-V processors facilitate that data movement in and out of SRAM into specific dedicated hardware for matrix and vector math. And that's kind of the math engine hardware. So moving the data in and out of the registers of that hardware and doing control flow and compute dispatch is really the core job here for those baby RISC-V processors. All right. So where are we going with this? We're trying to think about not just specific chips, but chiplets. So integrating a high-performance CPU chiplet, as I mentioned, that gives us this really great programming semantics. So you can keep those linear narrative programs that run operating systems and other key components pre and post-processing or integration with sensors. This is not going anywhere, and we're integrating it directly with AI chiplets or that AI 10.6 core. And you can also think about dialing in the correct type of memory, bandwidth, and interconnect, and allowing this to be more customizable for end-use applications, which have increasingly diverging requirements for all these different I/O and memory bandwidth concerns. Okay, and as I mentioned, going from Grayskull today to that chiplet, there's a whole silicon roadmap that at Tenstorrent we're building out. So you can look at, again, with Grayskull, which is generally available, the TOPS performance and the number of 10.6 cores changes as we go to Wormhole. The key difference here is we've added Ethernet. So we have 16 lanes of 100 gigabit Ethernet, and that allows us to easily scale out this architecture and use common components, which is another key theme. We've also increased the memory bandwidth with 6 channels of GDDR6. Then going to our next generation black hole, we're introducing a CPU onto the core or onto the chip here in the same package, and that's a RISC-V CPU. We've also 3x'd the Ethernet bandwidth, so 12 lanes of 400 gigabit Ethernet, and increased the memory density, so 8 channels of GDDR6. And you also note we've gone from 12 nanometer to 6 nanometer, so increasing density, adding CPU. That's a very interesting addition and allows this to be a more standalone ML computer. So you can look at a lot of that pre-post processing and operating system tasks directly on the chip. And then further into the chiplet future, we're looking at Quasar as our first AI chiplet, which is 4 nanometer technology and uses the 10.6 Neo core. So that's our large refinement of the 10.6 core architecture. And it uses these non-blocking die-to-die interfaces that are easily stackable. So here we go to Aegis, which is the high-performance RISC-V CPU chiplet. So that's 32 RISC-V CPU cores. So you can have up to 4 on a chiplet here. Also using the non-blocking die-to-die interface. So again, this really allows you to compose that right configuration of I/O, memory, CPU, and also AI acceleration for a specific workload, specific industry. All right, let's talk about the scale-out story. So today we have what we're calling our Galaxy server, which uses the wormhole architecture. So we have the Galaxy module. I should also mention we bumped up the Ethernet to 200 gigabit. That allows you to scale up with higher bandwidth. And I'll mention here, we're really trying to get to a world where we don't need switches, routers, host computers, or expensive HBM, so we can scale out with more commodity hardware. And another key point I want to mention, so Galaxy Server is 32 modules. You can put 8 in a 48U rack, and you can build that out into pods. But at the rack level, you start getting a very significant amount of SRAM. So with 30 gigabytes of SRAM, if you're thinking about a modern LLM model like Llama 3, you can now fit a very significant portion of that model directly into SRAM. So that allows you to do a lot of model parallelism and true pipeline parallelism to improve performance in terms of latency and bandwidth. As well, you have a very sizable amount of memory, so whatever is not on SRAM at a given time, you can have in memory very easily. Okay, let's talk about the open ecosystem we have in open source. So TT Metallium is our low-level kernel programming environment, and that was open source back in December. So if you're familiar with writing C++ kernels, that's really where that happens. We also have our Grayskull dev kit. So this is 2 boards, both PCIe, so E75 and E150. And we have E150 available on lab server. So if you want to get access, Yassine can help you with that. We also have the TT Buddha software stack, open sourced in January. And that's our top-down AI compiler. So if you're familiar programming in PyTorch, or you just have a bunch of existing model implementations, for example, if you just got off Hugging Face, it's probably going to be in PyTorch, somewhere in JAX maybe. We compile those down kind of using an internal representation of that compute graph, and you can run it on our hardware pretty easily. All right, and the open source does not stop there. So we actually have our system software also open source. And I encourage you to go to the github.com/Tenstorrent. So here we have a bunch of public repositories, and you'll see stuff like the system management interface, the kernel module or the kernel mode driver. So that's the OS level interface. We also have the user mode driver. So that's the application interface to the hardware. And all of this is open source, hackable. You're free to fork, open issues, talk to the growing number of Tenstorrent developers. We also have the firmware flashing utilities and firmware. So all of that is made available and as transparent as possible, allowing for anyone to kind of talk to everyone else who's building on this platform. All right, so the Buddha stack, as I mentioned, is our AI compiler. And you can kind of think of it as you start with that compute graph. So at the center here, you see a ResNet 50 graph or a portion of it. So these graphs get pretty big and unwieldy pretty quick. But we're actually able to compile that down, and you'll see the overlay here of the solved place and route problem. So this is an overlay of cores, which are 10.6 cores, and the corresponding operations. So in the TT Buddha repo, we also have some dependencies. So there's TT TVM, which is our fork of TVM, which is another Apache open source project that we use as our intermediate representation. We also have the TT Buddha backend. So that is the actual runtime engine that choreographs, schedules, and runs the binaries of all these different operators onto the chip. I should also mention we have a benchmarking repo. So we have a bunch of Python scripts that allow you to kind of do the 0 to 60 on our hardware and run with TT Buddha a bunch of known good implementations. And you can run not just for performance, but you can also look at the accuracy of the models. And you can vary parameters like data formats, batch sizes, etc. And you're able to compare with other hardware. We also have TT Buddha demos. So this is our growing list of model implementations. And we actually have some bounties out for people to add new implementations. So we're waiting for someone to collect the Fuyu 8B demo or the actual bounty for that. All right, and then TT Metallium is our low-level programming model. And this is, again, the kernel programming experience. So we also have a bunch of dependencies. The low-level kernels for Grayskull and Wormhole are available open source, and the SFPI. So that's the interface to our vector engine. So if you're used to, say, programming in PyTorch, we have a library called TTNN. So our engineering team has built this out on top of TT Metallium. And this is very intuitive, has a lot of very performant model implementations, and our team and a growing team outside of Tenstorrent is really working hard to make those pretty seamless and easy to use. If you want to go one step further, you can start optimizing those models and those implementations. So you can experiment with, again, stuff like batch sizes, different types of parallelization, data formats, sharding of tensors, etc. So you can kind of go deeper and deeper into the low level. And then at the very lowest level, at the expert mode, you can write your own kernels. You can start doing things that are not at all AI ML heavy. You can start doing HPC. You can do really whatever you want. Every piece of the hardware is programmable. Okay, so at this point, I'll open it up to questions, and I'll tell you a bit about, we've got our Discord, which is open for anyone who wants to ask questions quickly and get a community answer or an answer from a Tenstorrent staff member. We also have our docs website. And we're working on releasing a lot of our software also with containers to make things even more portable. And if there's any questions people have later or they want to talk about something offline, feel free to contact support@tenstorrent.com or you can email me. Yeah, thank you. Are there any questions or anything in the chat?
Thank you, Tom. So we are offering Tenstorrent AI accelerators at CMC, and we are supporting the software stack that Tom described today. If you have any questions, you can reach out to me or to Tom. So maybe one question for you, Tom.
Sure.
In your roadmap, do you have any chips that will be used in IoT edge for very low power, like IoT edge devices?
Yeah, I think
the elaborate on the roadmap. Yeah.
The good answer for IoT and edge is Quasar and Aegis, right? So you want to be able to scale up and down on the size of these. We are working again with some partners on the IP side for even smaller edge devices. But this is really where we want to think about edge is at chiplets, and you can kind of think of one Quasar.
Yeah. And any application developed on these devices is easily portable to other devices of Tenstorrents. Or
yes.
Yep.
Yes, we want to keep that API either on the Metallium side. With Buddha, it's even easier, right? You could have your model developed in PyTorch, and you can bring it across not just our hardware, but other hardware. We want to make sure it's very interoperable, and our compiler is able to work that out.
Perfect. But thank you, Tom, and we will now move to our next speaker. There is one question. What are your motivation for using RISC-V ecosystem or processors?
Yeah, that's a really good question. I said we believe very heavily in open standards. And so I think the story goes that when Tenstorrent was figuring all this out, they wanted specific data formats, and other providers of core IP were not willing or able to provide that or provide it on a timescale that made sense. And like Tenstorrent has a really great team designing this. So there's a lot of good reasons to point us toward RISC-V and allowing that to flourish as an ecosystem.
Thank you, Tom. Our next speaker is Jonathan Dursi, Senior Solution Architect at Nvidia Complex AI Workloads. Jonathan's sessions on Nvidia GH200 Grace Hopper Superchip is set to inspire with cutting-edge advancements. Jonathan, the stage is yours.
Oh, terrific. Is everything working?
Yes.
All right. So hi, everyone. I'm Jonathan, based in Toronto. This is my first time here, so this is fantastic. We've already heard a lot of really great work on IoT edge and all the way up to rack scale. So I want to talk with you about something that's more on that sort of side of things, on the training and optimization side of that spectrum we saw, or one of the application areas we've seen. We've been talking a lot of remote scientific projects with remote scientific devices, where they have a machine room at sort of the near edge that has to handle a lot of streaming data. So I'm going to talk to you today about something that I've been working on and having a lot of fun with for the last couple of months, the Grace Hopper, and hopefully I'll make clear to you why I think this is a great device for these sorts of things. So it all starts with the CPU. So the Nvidia Grace CPU is the building block of these super chips. It's a high performance, high memory bandwidth, power efficient ARM CPU, 72 ARM cores here, ARM Neoverse V2, with lots of vector math. But what's more interesting to me than that is the Grace for a data center CPU is really a data movement machine. 3.2 terabytes a second of bisection bandwidth between all these cores. And then that's connected in turn to high bandwidth, low power memory, up to 480 gigabytes of LPDDR5 memory. So we get 500 gigabytes a second to the RAM. And then this package then is connected over our NVLink chip-to-chip interconnect at 900 gigabytes a second. So this looks like the GPU to GPU NVLink you might be familiar of for coherent connection to what else is on the other side of that chip-to-chip interconnect. And all of this is, for machine room data center work, extremely power efficient. So the slide here says up to 2 times perf per watt over today's leading servers. That's completely true. So I've seen this on workloads that the CPU and the RAM combined, you compare on real world workloads with whatever x86 server you want to pick and take 60%, maybe as low as 40% of the power for a performance that's at least comparable. So that's one of the building blocks. The other key building block is the NVLink chip-to-chip interconnect. So, and this is what we build these super chip fabrics out of. So rather than go over something like PCIe, so this is 900 gigabytes a second of raw bidirectional bandwidth, and it's quite low power because it's all on package, 1.3 picojoules per bit. So it's much more power efficient while being much faster and much lower latency than PCIe interconnect or something to tie these machines together. The speeds and feeds and power draws are cool and everything, but what's interesting to me about this is what it enables, which is a coherent view of memory across Grace CPUs or Grace and Grace Hopper GPU superchips. So we have the CPU superchip, super cool for, my background's in HPC from way back, so that's of interest to me. If you really need high memory bandwidth, high power efficiency, high data center density, and high just per core power, compute power, this is a great option. It's just two chips, 2 CPUs SoC. You can add PCIe cards as much as you like. I'll talk a bit more about the kinds of systems you can get these in later. But mostly what I want to talk about today is the Grace Hopper superchip, which connects in this cache coherent way a Hopper GPU and a Grace CPU. And what this enables is the GPU can now access cache coherently the 480 gigabytes of LPDDR5 on the CPU side. So the GPU has access to this enormous memory space, as well as its HBM3 or HBM3E memory. They're separate memories. You can't just CUDA mem-malloc 500 gigs of RAM on the GPU, but they are visible in a unified address space, and you can access them from GPU cache from CPU. CPU can ping, GPU can ping one of the, you can get access to something that's in CPU cache. It all just works. And this is, we're starting to see impact a bunch of really interesting applications across a number of industries. All right, so let's dig into this a bit. The Grace Hopper superchip, 1 GPU, 1 CPU, really easy to deploy, scale out, schedule. And there's a few different ways you can get these. There's one with, right now, that with 96 gigs of HBM3 memory on the GPU. One's coming up very shortly with 144 gigs of HBM3E memory, so more capacity and more memory bandwidth. And shortly thereafter, we're starting to connect them. Here's a dual node GH200 where the CPUs are connected over the CPU VLink, and the GPUs are connected over the GPU and VLink. So this is a single node, just like a 2-socket, 2-GPU node, one operating system, but a unified address space across. The GPUs have cache-coherent access to the CPU memory and vice versa. So they have access to up to 1.2 terabytes total of fast memory, either HBM3 or the DDR5 X. So on one of these nodes, whether it's single or dual, the whole thing is energy efficient by design. We can slosh power from the CPU to the GPU as needed, and the whole thing can be power tuned to particular applications. So energy efficient design, the system memory is 7 times less energy than DDR5. The Grace CPU, ARM-based, extremely power efficient, and the interconnect, very power efficient, high bandwidth, low latency. The nice thing about the power steering is you can set a provisioned power for the package, and if the CPU becomes idle, the GPU can increase its clock rate, pull more power, but the total power will stay within that provisioned power envelope, which is important if you want to take advantage of increased power but still have predictable operations. All right, so Grace Hopper, power efficiency. So what's it actually good for? So we already actually heard a great introduction. Models are getting larger. Transformers are becoming increasingly important, one of several important large models. But also, AI workloads are getting more complicated. So rather than training, especially on the inference side, when you actually want to do something with a model, rather than just having one model which you're constantly doing inference on, now these models are part of a workload that may involve other models, may involve data tables, key value stores, vector databases. And so how do you run these effectively at modest power, at a modest number of nodes? So RAGs, retrieval augmented generation, are something we've heard about lately. As an example, if we have a large language model, we also need to be able to access, say, the keys of the vector database, be able to quickly index and pull in relevant pieces of data to augment the generation. So we can, with a GH200, total 480 gigabytes on top of this GPU memory, all that's there. You can access it very quickly. Don't have to go out through a bus. Extremely fast. In addition, when you tie this in with things like active learning, so on the document retrieval, ingestion, and search side of this diagram, you often want to not just do this, pull from static databases, but you want to be able to tune things, active learning, as you go along, or you want these models that are in memory to be easy to update. And again, this having everything in fast memory accessible to the GPU is just a huge win. So again, we can see this especially with things like graph neural networks, which are starting to be important in a lot of domains. Also especially interesting in the context of things like retrieval, where you might want to use knowledge graphs. So here's it's a standard benchmark graph sage 100 million paper problem, training a graph neural net. Having access to this huge amount of memory that you can access randomly from the GPU is just an enormous win on this kind of system. So the larger the model, the more complex the environment in which you're using it. Those are really cases where the system, the Grace Hopper, really shines. These are starting to be installed. Quite a lot of quite a lot of systems are coming online now, often in the research space. Venado here is one of the first ones here. They just had a big sort of grand opening in their data center last week. Jupiter, Delta, these other ones are coming online shortly. Again, my background is on the scientific HPC side, coming into AI really just in the last 5 years or so. So numbers like this really, really speak to me. Again, we have lots of applications out there that either have enormous working sets and or have phases of computation where that are very good matches to the CPU and other phases that are very good matches to the GPU, and you'd like them to be able to compute in parallel, or at least to be able to transfer data back and forth effectively. The one that's most interesting to me here is the quantum applications, quantum Fourier transforms, or state vector simulations of quantum systems. Super memory hungry. You really want as access to as much memory as possible per GPU so that you don't have to scale over enormous racks of compute farms. And we can see here, this is the state vector computation. But tensor networks and their applications are also really interesting on Grace Hopper, because there's often complex optimization phases, which are maybe a little more naturally implemented on the CPU, and then the big number crunching, very natural to the GPU. And again, this co-computation, fast data, fast interconnect, super relevant. There's a Grace Hopper Superchip now available on Launchpad. You can sign up for this. You get an email notification when it's your turn on the system. We have a few dozen of these systems available, and you can run the guided experience. The quantum is one of them, as is some LLM inference and RAG assisted inference, but also the quantum application is actually here. Mainly, the main thing I want to cover here in the software stack is that this is a super cool system, but it does not, it is not, it mostly just works. So the Grace CPUs are ARM CPUs. The Grace systems are ARM system ready certified. That means, you know, your favorite operating systems work, your favorite infrastructure management things work. They plug in, and, you know, they work with your PCIe devices, whatever they are. They work with your BMCs. You know, I've had ARM CPUs here in my office for 5-7 years. Things just work, and this should absolutely be baseline expectation with software too. If our NVIDIA compiler, of course, freely available, works really well, but GCC and LLVM, which we actively contribute to, they just work. You just compile. GCC, anything later than 12.3 or so, works super well on Grace or the Neoverse V2 cores. LLVM, it just works. There's some, you know, use MCPU equals native instead of MArch or MTune. You might need a signed char if you've been depending on character size, char signedness. There's no worry about math or anything. I know we have an ARM colleague here on the call. ARM, it's lovely, just works. When there might be a problem here, we don't really want people, at least NVIDIA, we're not asking people to port to ARM, really, right? Your compilers, your libraries, we expect those to work. What might have to happen is porting away from some, say, x86 assumptions, or porting away from a proprietary compiler that has some proprietary compiler extensions. GCC, LLVM should just work if your code is dependent on x86 intrinsics. There's scripts to help you with that. This is not This is not we've seen very few researchers with big challenges porting their code. Certainly the Nvidia software stack works, and you can expect it to work. I just want to talk about the chip-to-chip interconnect for one more second. You don't need to do any special coding to take advantage of that. If you have a partly accelerated code, runs on the CPU and the GPU, that will just work. You don't need to do a thing to take advantage of this. This does provide the opportunity for additional optimizations, but it just works. And the fact that there's a coherent view of memory across the system actually makes it super, super easy to get started GPU accelerating your code, because you don't have to worry about exact memory placement right away. And that's it. There's a number of different configurations of Grace Hopper systems that are available. Something super interesting for the edge, sort of edge machine room, is you can extend these NVLink connections to an entire rack or 2 racks with the NVL72. And in the slides that I'll make sure it gets sent around, we have a whack load of resources, both documents and videos and case studies. And that's it. Thanks very much, everyone.
Thank you, Jonathan. Great presentation. A lot of resources. Any questions to Jonathan? Maybe one quick question. You mentioned that it's easy to port software to this new architecture. Have you encountered some issues with legacy software that were developed in previous generation of GPUs? And how did you deal with them?
So certainly not with GPUs. Certainly anything that ran on older Nvidia GPUs for sure just work. Anything that can be coerced to run on Nvidia GPUs, anything that's, say, using OpenMP offloading or OpenACC, that'll all just work. It's just a GPU. There's other cool things you can do with it, but it's just a GPU. So yeah, there's no real issues. And in fact, the older the legacy code, the more times it's probably seen a few platform evolutions over the years, and probably a lot of system-specific, like x86 assumptions have gotten shaken out of the code. Like give me a 30-year-old Fortran program. That's just going to work, right? It's maybe newer code that has optimizations for one platform and doesn't have an alternate code path. That's where maybe you need to add that extra code path.
Thank you, Jonathan. Since we don't have any additional questions, we will move to our next speaker. So Flo is a CEO of OpenHW Group, and he will be sharing in his presentation insights on industrial-grade RISC-V CPU IP, paving the way for groundbreaking innovation. Florian, you are live.
Thank you, Yassine. I hope you can see the screen and hear me.
Positive.
Perfect. Then, hi everyone. My name is Flo. I'm the CEO of OpenHW Group. Very happy to be here today in this AI workshop. I want to talk a little bit about RISC-V. RISC-V is what we are doing at OpenHW Group. So first, is it ready for industrial application? And then the second question, can you really design a chip based on an open source RISC-V core? That's what we are offering. And then last but not least, give you a little bit more overview of what the OpenHW is doing. So let's start with the first question. Can you design a commercial chip, shipping hundreds of millions of it with RISC-V? Yes, you can. As a matter of fact, RISC-V is already used today in a lot of applications. I want to give some examples. We have heard earlier about the iPhone, for example. If you're thinking about a smartphone, you will have RISC-V already inside. not in the main CPU, but in things like the Wi-Fi controller, Bluetooth controller, or the modems, partly in the MPUs, but also in the storage or in the touch. That's where a lot of, especially Android phones, are already shipped today with RISC-V. Another example where RISC-V is shipped is SSDs, for example. I took out some old picture from a SSD. You can see there are various CPUs. There is a main CPU. There is also a controller CPU for the interface. And then there is a NAND flash controller. And there are already various different vendors who are publicly speaking about having RISC-V inside, and not only one core, but also several cores. And now also AI is the big topic today. A lot of things is added to make this SSDs also more smart, to tag automatically data, to identify what it is and store it on different places depending on how likely the algorithm deemed it to need this information later. So there is a lot of change ongoing. Very common misconception is no one is using open source RISC-V cores today. That is clearly false. Problem is a lot of people use open source RISC-V in commercial ASICs. Unfortunately, not many talk about it, especially when you go to design houses who make custom chips, bespoke chips. They have a lot of RISC-V inside. For example, I took this from one of the Open Hardware members, a design house in France called Dolphin Design. They offer this platform where customers can customize the system on chip. There is an MCU inside that could be RISC-V. There is audio converters inside. RISC-V is used. And there is also a DSP processor inside. They call it Panther. And then inside the Panther, you will have multiple RISC-V cores, so you really can configure from 1, 2, 4, 8, 16 or more cores, depending on your use case. Interestingly, these RISC-V cores are used in, I would say, kind of hidden application. So it's not so easy to buy a MCU with RISC-V, also that is now more available on the market. But you will have a lot of RISC-V and things like SSD, where you're not writing a program, where you're just using the product as it is. Connectivity like Wi-Fi chips or so on, but also audio, wearables, earphones and so on, IoT devices. And the real driving point where we see AI is really AI where it's driving for RISC-V. That's also coming back to what the friends at Tenstorrent said. So I really like Tom's presentation, also pushing for RISC-V. Now, let me give you a short overview who the Open Hardware Group is. We're a global non-profit organization. We are registered in Canada, Ontario, and our mission is to host and curate high-quality RISC-V cores and in related IP for industrial usage. So we are really looking at what we are doing can be used in a commercial product. To achieve this, we are providing the infrastructure to host it, but we are also helping and coordinating the support for it. That includes development. We have a very big effort on verification. If you do a chip which costs a few million to tape out, maybe you need to be sure that there are no hidden bugs inside. So verification is very important for us, but also documentation, allowing other developers, universities, companies, whoever want to use the core to easily adjust the core and integrate it into their own design. Interesting and very important about the Open Hardware Group is that we are driven by our members. I would say there are 3 groups of members we have. Industrial members, that can be a company who makes a chip, academic members or a university or something, or also research. So CMC would be something, a mix between all of the 3, and CMC actually also one of our members, so very grateful for this. Just to give a very short overview about the members, and I don't want to go into the detail. You see names like Silicon Labs, Cyrus Logic, but also Case. Photosip is one of our members, Calray, Alibaba, and of course also CMC Microsystems. Industry members really doing products with our open source industrial grade RISC-V cores. Then we are having the academic members. These are really focusing and helping to do research on the chip, but also preparing products together with industry partners. So ETH Zurich are very strong. Actually, we inherit some of their open source cores and maintaining and verifying them now. Spain, the Barcelona Supercomputer Center, also working on high performance computing with RISC-V. And then University of Ottawa, but also University of Toronto. That is not an exhaustive list here. And actually, we are quite rapidly growing, signing up more and more new members. Then we are also having a partner ecosystem. Cadence, for example, but also Synopsys is one of our partners. Global Foundries is one of our partners. They are really helping us to move to the next level. They are providing us tools for our internal staff to help to verify. Now, the question is, why is the Open Hardware Group here? What we are doing and why we are existing? And that comes down to a very basic question. If you wanted to make a RISC-V chip, you had basically two possibilities. You could license a core from an IP vendor who is doing RISC-V cores. That could be maybe Tenstorrent, that could be Sci-Fi, or maybe Endis Technology. And you can, for a relatively low cost, license a very good core, but there is a limit for customization of the control. Even if it's RISC-V, the vendor provides you something, he provides support, but he don't allow you to modify everything. Now the second chance would be that you develop a custom in-house core. You can completely adjust it to what you need and how you need it. However, you will need to hire more people, not only to develop the core. Developing the core is actually the easy part, but verifying the core, and then in the long run, maintaining the core, adjusting if updates on the specification happen, adjusting things, simple things like the compiler, making sure your core is supported by the compiler. All this is a lot of resources which will bring the cost of a custom core quite higher. So this buy versus make decision is what you had in the past, and the Open Hardware Group is jumping right in here. We are offering a third option, which is this industrial grade yet open source cores. Our cores are under an Apache 2.0 license, so you can take them as they are and create a commercial chip, or you can use them for research, which actually a lot of people are using. So you have an easy entry point, your cost is relatively low, you just take it, you do it, but then you can go off and you can modify the core. You can add custom instruction. You can modify the pipeline if you want. So you have complete freedom, and depending on your budget and your time, on your manpower, you really can go and do a lot of interesting things with a core which other people already have shipped in commercial deployments. Now let me give you a short overview about the deliverables, what you can expect and get from the Open Hardware Group. So the core thing is really the RISC-V core. We have a family of cores. There are actually 3 different types currently inside. CVE2 deeply embedded, CVE4 embedded MCU, and then the CBA6 an application ready CPU where you can run, for example, Linux. License for all of these chips or RISC-V CPU cores is Apache 2.0 with SolderPad on top. So SolderPad is just defining some words for hardware design, what is an RTL and so on. Basically, it's Apache 2.0, makes it very easy, especially in industrial or commercial applications, because the lawyers already use Apache 2.0 software that is established in the industry. So having some hardware following the same license is very easy. The cores itself are written in System Verilog. That is very important to make sure that it's easy, adjustable, and usable when you're integrating it into other systems. Now, the core itself is very important, but the core is nothing with verification. For this, we are also providing open source verification test bench written in UVM, System Verilog 2.0. They work with all the major EDA tools from Siemens, the Questa or Siemens Mentor, the Questa, but also from Synopsys, VCS, from Cadence, and many other third parties who are supporting this. Of course, verification, you're good to go, but you're still missing some software. So we are also maintaining the basic software, compilers like the LLVM or the GCC, where we have upstreamed our cores, so all the features we are having, which is the basic RISC-V, but also some custom extension to speed it up, like hardware loops or packed SIMD extension. You can switch it on and off, are supported by the compilers, upstreamed by our members to the open source. There are various different real-time operating systems which are supported and run on our cores, and also Linux support is ongoing. For example, one of our members is also Red Hat. Now, of course, verification, software, documentation is super important for all of this. You need to have a good documentation so that you can integrate it in your projects, that you understand what was the design idea behind, and also to easily check what are the possible parameters I can use with this. And last but not least, we also provide some FPGA board images so you can do a quick performance analysis or something like this. And we are also working on some SoCs. I have more on the following slide about that. Before we jump into SoC, I just want to show you our roadmap. The roadmap ranging from the deeply embedded cores. You could compare it with an ARM M0 Plus, roughly, depending on how you configure it, but they are really small, low power consuming. Then we have our CVE4 family, which is more like an MCU kit. There are a lot of different cores inside this family, so the spectrum of performance is also quite big. And then we have the CVA6 family, which is our application-ready processor. There are quite a few different projects inside. These cores are also under tape-out currently. Actually, also CMC Microsystems is helping to tape out the chip, which is Linux ready for this. Then last but not least, there's also a CV Volley core, which is used in the textbook from Harris and Harris, how to make a CPU, so detailed architecture description, and that is also target for industrial use. Now, we're also planning for the future to have something more high performance. Just give you a rough overview about the roadmap. Now, coming to the chip, and that is really awesome. We are a non-profit, so we are financing ourselves with members, and we are working with and for members. We came together with some of our members and we made this chip. So CMC Microsystems has helped us to make the RTL to GDS and then also handling all the web fabrication together with Global Foundries. Global Foundries is a partner or a member of OpenHW. They have helped us and sponsored a shuttle in 22 nanometer FDX process from them. Inside the chip, of course, our RISC-V core. One of our partners dropped in an embedded FPGA for test reasons. And then another partner has contributed PLLs and clock reset generator. So quite a nice system. The Amazon team has helped to port FreeRTOS on it with all the drivers for the IOs and so on. The whole system you're seeing here is freely available on our GitHub. The core itself is high quality for industrial usage. We are calling it TRL5 from a quality level. The system itself is TRL3, so we are certain it will work on a prototype. And yeah, the AI accelerators need RISC-V. That's the one thing we are sure about. because RISC-V gives the flexibility to add, to remove, to fine-tune whatever you need in the core. Tom at Tenstorrent has shown this very nicely, where you really can add it, where you can add several cores, like 3 cores for a matrix multiplication and other cores for the system. So that is really the big benefit for RISC-V, that you can fine-tune the cores as you need. You can add custom instruction. You can add closely coupled matrix multiplicators or something like this and save a lot of energy by doing so. There are a lot of startups in AI. A lot of the startups are using RISC-V. Sometimes they use it together with other architectures which are established on the market, and they still have a good benefit. But if you're working on something with AI, especially accelerators, you really should look into RISC-V. And here the OpenHW Group is an open source provider, however with industrial grade, so fully verified, fully documented, with members from us who are shipping real products. In total, just to throw in a number, we know that our cores have shipped in over 500 million devices. That is quite a significant proof of quality, saying that that really can be applied to industrial or to commercial applications. With the cores from OpenHW, you can give your designers some head start. So they take a core which is known to work and then focus on your application, add the accelerators you're planning, or focus on a spiking neural network. Whatever your target, your project is, the core will give you more time to work on the real important thing, on your differentiation. That was a very high-level overview of what the OpenHW is doing. So please feel free to check us out on openhwgroup.org. Find us on the email, so feel free to drop me an email, flo@openhwgroup.org, LinkedIn, Twitter, you will find us there. And if you have more questions, also CMC, they are a great member. They have worked with us not only on one chip, they work also with other members to tape out other chips, so they really know how to use our RISC-V cores. You're in good hands.
Thank you, Flo.
Would it be from my side?
Thank you. Great presentation. It summarized it all. I think researchers love RISC-V because it's open. They can modify the cores. They can perform research in hardware, software. So there's a lot of flexibility there. It is also an attractive alternative for startups, especially those coming from research lab, from academia.
Yeah.
I think,
fully agree with you, Yassine.
yes. We have a question here. Is there any interest in developing university-level educational lab kits developments, if it's not already available?
Depends how you're defining it. So I liked your addition if it's not already available. Like we do have this one core, the CV Volley, that is already used in the textbook from Harris and Harris, that is really target for undergrads or graduate students to learn the microarchitecture, how to design a RISC-V core. It's a 5-stage pipeline which also can run Linux. So you really get all the details. I think that it's a great starting kit for teaching. And then we have the other thing, like this chip you're seeing here in the picture, that is made available to our members on request. So from time to time, we are running projects like this where we say we work together with members, and then other members like universities who are members of OpenHW can also reserve 1 or 2. And then there is also the third possibility where members like the university, I'm not sure if I'm allowed to say the name, so maybe I better don't say. But anyway, there was a university making a chip which can run Linux, and then CMC also has helped to make the backend and the fabrication of the chip for that. So there are a lot of different possibilities. Again, the beauty of open source, you really have a lot of freedom to do and to innovate.
Great. For the attendees, you can unmute yourself and ask questions directly. I think you can do that. Otherwise, you can ask questions in the chat.
I don't see Ethernet on the taped out like block design. Does it support Ethernet?
This chip, that was the microcontroller level, so here is no Ethernet. That is really something small. If you would compare it to an ARM, it would be maybe on something like an ARM M4, M4F with floating point unit. There is additionally some packed SIMD instruction inside to speed it up, but there is no, there is no Ethernet inside. However, that could be possible, especially if you're going more for the Linux devices. At the OpenHW Group, at this time, we don't have an Ethernet IP.
All right, I think we are 5 minutes late, so it's time to take a break, 10 minutes, and let's come back at 2:40. Let's take 5 minutes this time, and we will resume with Bill Jenkins from Untether AI. See you in 5 minutes. Thank you. Welcome back to Accelerators AI 2024. So up next is Bill Jenkins, Senior Director of Technical Marketing at Untether AI. So Bill will unpack energy-efficient AI inference acceleration, drawing from his rich experience spanning hardware design to business development. Bill, the stage is yours.
Great, thank you. Let me just share my screen here. Oh, get this out of the way. Okay, perfect. So what I'll talk about today, as you've seen it said, is kind of what we're doing at Untether AI, specifically a little bit about Untether AI. We're a startup company, been around since 2018, mainly located in Toronto. We have quite a larger contingent of people as well in Silicon Valley, although I'm out of Massachusetts, so we are all over the place. About 170 employees total, a lot of investment capital from people like Intel and Radical Ventures. But our whole goal is to basically help companies execute AI workloads faster, cooler, and more cost efficient. And we do that through at-memory computation, which I'll talk about a lot. And we are effectively a semiconductor or a silicon company, right? So I'm sure everybody's seen slides like this, or this slide specifically too. The whole idea is that the growth of workloads, especially AI workloads, it's just growing at a scale that's far greater than Moore's law can sustain. So it's really about heterogeneous compute. How do we keep up with this ridiculous scaling especially for generative AI with transformer models? And that's kind of the principle behind what we're looking at. And so we have multiple devices today, Run AI, Speed AI, and then we're introducing other future devices as well. And the idea is to kind of expand the capability of what we can accelerate. And I'll kind of explain how that helps everybody in some sense in a little bit. But the idea is to kind of get from the old school compute-bound models to what are now definitely the memory-bound models with these very large transformer models, trillions of parameters. So the problem with that is, or these very, very large models, as we all know, is power, right? So the growth it's growing at a rate that is you would argue is unsustainable. So you look at 2023 to what they're forecasting in 2028, over 4x, kind of power consumption growth. AI going from about 4.5 watts to almost 19 gigawatts, I should say. And if you look at a data center, from 8% today to 15 to 20% of the power consumption of that data center for those kind of workloads. So if you look at that, that's almost unmanageable going forward. And what we're seeing today is a shift, or forecasting a shift from being centrally located compute to the edge, right? We all understand why edge is so important. So that means that efficiency is kind of becoming a first order design goal. With data centers consuming 1 to 1.5% of the world's power today, putting out over 300 metric tons of carbon dioxide, and again, expecting a 2 to 4x increase in percentage by 2030. So we need more energy-centric approaches to solving these systems problems, both board servers, data centers, but also specifically the workloads of artificial intelligence. So the way that we approach this, and what I'll show in a second, is the chief culprit tends to be data movement, right? And especially this is true in neural net inference. And what we focus on is inference specifically. So to kind of put that into perspective, if you look at where most of the energy is spent, it's not in the computation, as one might initially think. It's actually in moving the data. So if you kind of look at this yellow at the top of, again, all the different layers of a neural network, and you look at the yellow components of all those graphs, that's your compute. Everything else is data movement, right? So for CPUs and GPUs, computation is actually a very small fraction of that power. The idea is that every clock cycle, you're spending that moving data from memory to, you know, the compute blocks and back again. And so that increases latency and increases power. So how we address that is basically to minimize and localize the data movement. And I'll get into how we do that and what that means to other people. But there's two ways we approach that is inside our chip. So our chip is at memory compute, and I'll explain what that means. And you can see just looking at a standard GPU, drawing 690 watts to do this, we can get that down to, you know, about a 12x reduction in power. And the other thing that I'll talk about is the I/O component, which is how we manage it outside the chip by basically using this as a chiplet. We can get a 40x reduction in power, in the I/O power, using the chiplet concept. And what does that memory compute mean? Well, what it means is you look at a von Neumann architecture and you've got this hierarchical memory with external DRAM, you've got caching, you've got your logic, and you're pipelining the instructions, fetch the data, write the results out back and forth. And it's not that we're slightly different, totally different. It's that all we did is place SRAM in the compute. So when you're actually performing the compute, you load all your activations, all your weights, you perform the compute, and you store the result localized to the ALU, passing it to the next ALU for its computation, and back again, and back and back and back. So it is what we call at-memory compute, because the compute and the memory are tightly coupled together. Now, we still have external DRAM for storage, especially when you get into very, very large language models that need, you know, tens of billions of parameters or hundreds of billions. You have to rely on external DRAM. But the idea with this is we are minimizing the need to go off chip. We're minimizing even the need to go far in the chip. So we're actually doing very quick writes from one processing element to the next. So what that looks like from our perspective is kind of a mix of SIMD and MIMD capabilities. So our architecture is a spatial architecture. So we have what we call memory banks organized in a matrix, a grid throughout the device, interconnected with hardware NOCs and I/O ring NOCs. So making it very easy to move data throughout the chip from one element to another. And unlike a GPU that's kind of a warp block SIMD architecture, we are and can be whatever you need it to be. We can load the instructions, load all the layers at once, right? We can even add multiple topologies in that architecture at once. And so the idea is that you can have different levels of parallelism, both instruction level and data parallelism. You can have multiple, say, camera feeds feeding into the device, however you want to arrange it. But the idea is that these memory banks are made up of, and there's two RISC processors. We've been talking about RISC processors, RISC-V processors that kind of control these arrays in the memory bank. So there's two RISC-V processors control, effectively 64 of these rows, and there's 8 rows. There's 64 processing elements per row, which gives us 512 processing elements per bank, and that's over 372,000 processing elements per chip, which means, doing every other, you can do 2 multiply accumulates per cycle. You're basically doing, 744,000 every cycle, multiply accumulates. And so again, a different view of the PE array. You're basically getting data from somewhere in the chip, whether it's from external memory, whether it's from SRAM, whether it's from a neighboring PE, but they're stored in a register, multiply accumulate occurs, and then you write the result again out to whatever processing element is doing the next compute. And that's all done, every clock cycle. So in our case, batching doesn't necessarily make sense. So we can actually perform very, very low latency compute and very power efficient and utilization of the hardware. So we get nearly 100% utilization of our hardware. Okay, so what that means, the first, Speed AI is kind of our latest device. That's the one that just came out this year. We also have Run AI, which I'm not going to talk about for this purpose. But Speed AI, we have a packaged part. It's about 2,000 teraflops, 2 petaflops. It's realistically, it's probably in the 40 to 70 watt range, depending again on what you're loading in and what you're doing with it. But the other key that I want to take away is that's great. We have a part, you can use that part. But what we also see, to tie back to that original slide that I talked about heterogeneous computing, is the chiplet structure. So this architecture comes in different flavors, smaller variants. So if you needed less banks, 479, 242, 18, the whole idea is that you can use these chiplets in your architecture for your SoC ASIC that somebody could be building. So again, to solve this problem is, sure, we have a chip, you can use the chip, you can place it down with other devices on a board, you can use our boards, as I'll talk about too, but the real benefit here is the chiplet structure, where we can place this in an SoC with other devices. I think the B1, well, certainly the B2 one we label here, that's definitely automotive qualified as well. So the idea is to target specifically edge applications. So if I kind of look at the Speed AI architecture like I showed before, it's 728 RISC-V memory banks. So you're looking at 2 petaflops of what we call FP8 compute, and we have different formats that we support, all the way from int4 to floating point 16. And we can get into details at any point about quantization to FP8. I actually just published a white paper where we actually talk about how our accuracy at FP8, we don't really lose it, going from quantization from FP32 down to FP8, and then using int versus FP. Int versus FP is, for our purposes, negligible. We actually are more efficient at FP8 than we would be with int8, although we do support it. So again, 1,456 RISC-V processors running anywhere scalable from 700 megahertz to 1.3 gigahertz. That's about 30 teraflops per watt. With all that SRAM that we have in all the memory banks, it's about 238 megabytes of on-chip SRAM. And then, of course, we have external DRAM as well. We have multiple banks of PCI Express, so that we actually, as I'll show in a second, we have boards that have 4 of these devices on a board, and then you can interconnect boards together. So we use PCI Gen 5 by 8 to do the chip-to-chip communication and scale this out across multiple devices and multiple boards. And then PCI Gen 5 by 16 back to the host. And we have 2 banks of external LPDDR memory to do kind of your external storage. But of course, we have packaged devices like the one I showed you, but also those chiplets. So those will come, in your standard BGA package with your PCI Express interface. But what we can basically do is take that packaged device that uses an implementation and replace the PCI, or basically it's still there, the logic is still there, we're just turning it off, and switch to UCIe and offer that as a chiplet so that people who want to put this in their ASIC can do so using UCIe. Now, and UCIe 1.1 specifically today. And the whole idea, hopefully I don't have to explain this to everybody, you guys understand the benefits of chiplets. And this is a list, I don't need to go through it all, but I think we all recognize that scaling is having kind of optimized performance for specific tasks using dedicated hardware is a good thing. Trying to do that in a way that allows us to not rely 100% on these on the more less power efficient, more power hungry devices, and offload the things that we can offload to the more efficient hardware is one of the ways that chiplets can be leveraged to kind of try to address that the power conundrum we're running into. So we also, because again, compared to monolithic, you can get slightly higher integration, lower cost, higher yields, things like that too. UCIe vision, right? The actual UCIe interconnect standard. They all believe in an open chiplet ecosystem. I believe most people are trying. I think there's a couple competing
protocols to move data between chiplets, but the idea is we need something that's heterogeneous integration to connect a particular die to another die. And this is even the direction that we see that UCIe community sees it's going to happen, is people need to have these chiplets that allow us to build these SoC kind of devices. So what does that mean to our architectures? Well, okay, so I just picked a couple of different vertical markets that I'm involved in. So you look at like electronic warfare, where you're doing some kind of RF sensing on the front with an ADC DAC, and you feed that data that you're collecting into the AI accelerator that has memory in there. Maybe it's HBM memory in the device. So then maybe you have an automotive system where you have the CPU. You actually have an I/O hub to do, sensor integration of potentially many sensors, many cameras even, feed that to the AI accelerator, all within the same package, the SoC, or even in the server space. So even the data center cloud environments, you can put the CPU and the AI accelerator in a package and again, deliver a board that can be used for AI in a data center cloud environment. So this is just a couple of high-level views of the models that and there's obviously many more and many people doing these kinds of things, but how are AI accelerators being used to integrate into someone else's ASIC? So as I said before too, we also sell packaged parts, so you could do chip down design. We also provide boards. So the idea is that the Speed AI 240 device, you can use it as a prototype for the chiplet version variant. It's the same software, it's the same flow, same architecture. It's just potentially smaller. So you can use that to prototype. You can also go to production with it. So this is just a kind of a 75 watt card with 2 petaflops of compute capability, PCI Express card. We have half height, half width. We have both active and passive cooled solutions. And then we have the 960 card, which is basically a card that uses 4 of those devices. So now you're talking about 8 petaflops of compute on a card. That card is about 300 watts. It's basically 4 of those chips. And so this, as I said earlier, is also scalable. So use these connectors across the top. All of these chips are interconnected through the PCI Express and also off chip. So you can cable board to board to scale this across an entire rack. So as I said, the software is you can't do much of this without good software flow. So we have an SDK called the Imagine SDK, which allows you specifically to go from TensorFlow, PyTorch, whatever, and we offer a model garden as well. But to take those models that are already pre-trained and done, and then we'll ingest them into our into our flow, do quantization on them, again, for the different floating point integer formats. Usually people obviously train in FP32, and you can easily quantize to FP8 on our device. And then because it's a spatial architecture, and again, you're controlling how you're mapping, what layers you're mapping, where you're mapping the layers, how you're moving the data. So you're basically building a processing pipeline in our chip. So we have a compiler that does all that. It basically manages compiling, to an LLVM, managing the whole creation of all the logic, and then actually placing and routing it. Similar to how FPGA is, if you can conceptually think of FPGA as another spatial architecture, but it basically builds that architecture on our device. And then, of course, the runtime to run it with a simple set of APIs to communicate with it. So that's kind of the key thing, is that, yes, this is great. We have the hardware, but we also have a software flow that's both compatible with the chiplet path and also the chip, packaged chip path. So last slide is just basically, you guys want to use it, it's available. We have parts today you can order, boards you can buy. And of course, just register and you can get access to the SDK if you guys want to play with it. I believe, Yassine, too, you guys have some of the older boards, the Run AI ones.
Positive. We have at CMC Untether AI Accelerator available for research to academic. I have a few questions here. Jonathan, is Untether interested in open sourcing the software stack like Tenstorrent?
Yeah, that's a big question. initially, I would say we're open to anything and we would talk about it. I would say that's a great conversation that we can have. Obviously, right now, being a startup, open sourcing is not our optimal decision or choice, I should say, because there is obviously a lot of proprietary things to our architecture and how our software does it. But that doesn't mean that there aren't things that can be open sourced to make it easy to connect to our software. And that is certainly something that we would be interested in talking about if you guys want to. Also,
is there interest for Untether in research collaboration with universities?
Absolutely. I am a big believer in university collaboration. I would say initially, because we're still early, I mean, our major focus is obviously winning more customers and generating a larger revenue stream. But I also see the value in university research, getting university people familiar with it, using it. And hopefully even, you get a lot of collateral out of that. You get a lot of research out of that. You get good feedback out of that. So I'm a big proponent for that. I believe this year I have permission to collaborate with at least 3, if not 4 universities for that purpose. So we have cards and licenses that we will provide, and definitely interested in talking to people.
I have a question or comments from Flo, the CEO of OpenHW Group.
Yep.
So it's a great presentation. Just wondering if you can elaborate more on the RISC-V core you use. Is it a homegrown core or it is licensed core, or maybe an open source core? So.
Ooh, that's a good question. It's definitely not homegrown. So, and maybe I should preface, I've actually only been at Untether for about 2 months. So I'm still learning some of the history of that. I believe it's a licensed core, but I could be wrong. And then I guess what was the other question? Part of that is how are we using it?
Is it licensed core or open source core? Yep.
Okay.
No, so Bill, the question was more like what kind of core it is. If it's a licensed core, that kind of answers it. Maybe you could look into an open source core like OpenHW, but we can take this offline. It was just interesting, and I really love to see RISC-V inside and cool presentation. Thanks.
Yes.
Yep.
These are 2 success stories of using RISC-V in commercial products, Tenstorrent and Untether. We are very proud to collaborate with you. So just to keep this flowing, we will switch to our next presenters. Thank you very much, Bill. And now it's time to introduce our next speaker. Stephen Su, Senior Product Managers at ARM, will shed light on transforming AI with ARM Helium technology, unlocking the potential of Edge AI. So, Stephen, the stage is yours. Please share your screen.
Yeah, I am sharing.
And you are on.
Okay, I assume everybody can see my slide. Okay, so I just go straight to my presentation. Hello, everyone. My name is Stephen. I'm Segment Marketing Manager. Very glad to be CMC Microsystems workshop this time. Today, my presentation will be focused on ARM Helium technology, and me and my group, we focus on Edge AI. We also construct reference design, so also cover hardware, software. I make a simple introduction here, so let you know how we can help you to your Edge AI journey. Next slide, please. So just very quick about myself, left-hand side. Right now, I'm in their IoT line of business group. This is my email, and also link it if you think you benefit for you. Welcome to contact with me. In the left-hand side, right now I focus on their CPU, NPU, and ISP. We are an IP company, but we don't only focus on IP. We also make like sensible combination of those products as a reference platform to help our customer. So if you think anything would be helpful, then welcome to contact with me. Next slide, please. So everybody know Edge AI right now basically everywhere. But I think it's still good to introduce some use case that we see from the market to you. For example, everywhere, but specifically in smart home, you can track your delivery or check the baby or check the pet. And also we see more and more important vision application or product in the battery, especially in the battery power. Because when you deploy that either in your home, your office, usually people don't want to have like worry about how to arrange the power cord, those things. So we think there's a trend for battery-powered product that getting more and more important. And also this kind of product will also use at the building as well, and also some like access control. I think people right now more and more they think privacy, security, this kind of thing is more important. So we see the trend on the access control as well. And then nowadays, I think almost everyone have like smart doorbell or smart door lock. This kind of application is getting more and more as well. So overall, all of this you can see it's everywhere, and also you need low power for those battery power device. So I think all this application can run very well if you have like energy efficient, especially on the MCU type of IP. Next slide, please. So first, it's everywhere, of course, and the second thing is how the product, the computing core itself evolve. So we think that many reasons here to drive the endpoint to be more and more intelligent. For example, previous concern is first one, and then as I mentioned, power, latency, and also the autonomy. The reason is from people day-to-day life. I think probably everyone have the same experience. Your internet doesn't work, or sometimes some technical issue happen. So that's the reason I think that would drive the more and more, the edge AI device will be more and more like intelligent. So the next question will be then how, as I mentioned here, how to deliver like a high performance and also the efficient machine learning on the MCU type of device so that can match what you need. Next slide, please. That comes into today's topic that I would like to introduce is our Helium technology. You can see a link here. It's actually a reference book. It's clear reference book to tell customer what is the technology that is used here. So we call it Helium. Basically, it's our brand name. Naturally, it's a vector processing instruction set. I think many people are familiar with computer architecture would know what SIMD mentioned here. It's basically a single instruction, multiple data. So Helium is our brand name, and this kind of SIMD vector processing, we put it in our V8.M architecture. So what we call it 8.1M is because it's in our Cortex-M vector processing extension. We also call it MVE. So the Helium is equivalent to the MVE mentioned here. To explain it in very straightforward way, is like it's our Cortex-M extension focus on vector processing and on our Cortex-M MCU. So the goal here is mainly to enhance the performance uplift for the DSP and also the ML performance improvement. So our target, actually right now we have silicon, we can increase that to be up to 2x data path increase, and also I put the 4x here uplift in DSP and machine learning performance, but actually in many cases we can see it's more than this kind of 4x uplift. So that is the Helium technology. Next slide, please. Just get a step further into what is the technology mean. So we typically in traditional how the computer, especially the CPU works, is like you have one instruction and that only goes to one element within the one lane. But now with the SIMD single instruction multiple data, I think the name explains itself. You have single instruction, but that single instruction can actually apply to many lanes. As I mentioned here, it counted by like element. You can see like one lane by one lane control, but apply to all those lanes together. So you can see we actually bring this kind of technique onto the MCU and to speed up machine learning and DSP type of workload. So control by the element and control by the lane. What's to mention here is you can see that Q register is like a very long register, like we have 128-bit, and how many lane here, how many element that long register can control actually depend on what is the the length of that each data, should say the elements data type. So there is 32-bit, like 16 if you use 15 floating point 16 or integer A. Of course, shorter the data type, you get more length like you can use. Next slide, please. So how to use the technology? Technology is great, but how to use it? First, I will start a CPU core. You need a CPU that enable this kind of Helium technology. So introduce you the Cortex M85. This one can really bring you that kind of image not image, the workload, the performance enhancement in the MCU. So you can see for this one, it's just a simple block diagram. Helium technology is enabled in Cortex M85. This core is our right now highest performance one. Performance is one thing, but also you can see there is a built-in trust zone or some optional security mechanism there that could be an option for our customer. Next slide, please. So not only Cortex M85, and we not only enable Helium in that kind of CPU core. I think from our perspective, I know scalability and flexibility is important to our customer. So actually for Helium, that is the product family. You can see we have high efficiency one, which we call it Cortex M52. And we also have the mainstream one, which we call it the M55, with the number getting larger. You can imagine that performance getting higher and higher. And also one, the core that I just introduced, Cortex M85, which is focused on the highest performance. So that actually is a scalable type of CPU core that we can offer for our customer to choose, that you can have high efficiency one, mainstream one, and also high performance focus on the machine learning. Yeah, next slide, please. So that is the CPU core itself. As I mentioned, our job is to facilitate for this for our customer can easily use it. So CPU core is one thing, and how about others? For we also offer our reference design. We call it Corestone. You can see here on the headline topic is Corestone 320. So with the Corestone, it's our reference design. So what we offer? So from left-hand side, it's integrated with a selection of IP. So there's the Corestone Cortex M85 that I just introduced. Of course, in the center there is the Ethos U85. That is our micro NPU. Right now, because AI machine learning is so popular, we also offer this kind of design is the CPU core and plus the NPU. There's also other core as well. If you are focusing on vision and computer vision, we have Mono C55 image processing unit here. We start, it's not only IP that we provide. We have interconnect or system IP, debug, hard coverage, debug, security, power control, all those things. So this is our IP that we offer on the platform level. But we offer more than this. This is just hardware. In the center, you will see we also have many collaboration with our ecosystem about the software, about the tool. So there will be like a reference application, there will be other framework, there will be middleware as well. In the down slide, I will give you more example what we are offering. And move on, there is a prototype platform. It's fine. We just there is we call it virtual hardware. Basically, it's like a model tool that we host on the cloud. So our users don't really rely on the hardware. They can use virtual hardware to do their simulation or their early software bring up. And we also have virtual platform and also the APG as well to provide to our customer. Yeah, next slide, please. So that is overall platform level what we are offering. This one is specifically for the software that we provide to our customers. So we can see stuff from Corestone. In the tool side, we have Kyle that work largely with like a VM or other compiler. And also we provide reference application in our developer.com. There's keyword spotting application or speech recognition or object detection. Those are quick and easy example to help our customer to get into this ML world quickly. Other than that, of course, we also have a standard. This standard is more focused on, we call it PSA, is focused on the security. So overall, I think we have a very strong software offering here for our ecosystem and also for our customer. Yeah, next slide, please. So that's software offering. Right now in the ML world, everybody knows the open source resource is important to everybody. We also, of course, offer open source library in this space to supporting the Helium technology that I just introduced. So you can see button there, you will see a couple link to the GitHub, which is those open source library that we provide. Synopsys, which in the later on slide, I will make more introduction, but here we'll focus on, I think for DSP and machine learning, important one is where is the library to help you to speed up those applications. So we will focus on CMC DSP, the stream, and NN here means neural network. CMC is like our common software standard on the Cortex-M space on the MCU. So you can use DSP, you can use stream, you can use NN to speed up your application. For the stream, basically it's like a scheduler. So now in especially machine learning, it's one stage, then one stage, then one stage. So you can see that actually is like streaming processing. Then we also have software library to help you to handle this kind of workflow. Finally, we also offer another library called ARM2D. You will see more and more application on the MCU side. You need a graphic to show you the UI or some either is some like blending for the control that or showing some important information. We also have open source library to help you to reach this kind of application. Yeah, next slide, please. So we go over the hardware, CPU, and the platform offering, then also the open source. Now we give you a concrete example that we, well, I think ecosystem collaboration is getting more and more important in the ML world. Now it's very difficult for just one company to fight alone. We partner with OpenHW. They are famous in the maker market. And they produce small, very size, like form factor size camera. You can do many interesting computer vision type work on their small device. So start from Helium, and Helium enabled in the core I just introduced, like M55, 85, with called OpenHW their library, so that we can enable many interesting IoT edge device to be like computer vision aware. The impact will be twofold. First one is by using this, we can really bring high performance computer vision into very low cost device and very, very low power. And then either is very, very low power, but we can't, because this kind of performance uplift, you can really reach that to the high resolution. Don't need to limit it to just VGA or even small size. We can bring the computer vision resolution up to HD or full HD, this kind of size on very, very edge device. Yep, next slide, please. So that basically go over what we offer in the edge AI device in terms of like DSP, machine learning, or computer vision. Here I will just go over more support in the AI on the Cortex-M side. Yeah, next slide, please. So Synopsys, I know I mentioned Synopsys DSP, which can help you in the DSP type of computation, and Synopsys, and just one slide to give you a more like whole picture what we are offering in this space. So Synopsys, the full name is Common Microcontroller Software Interface Standard. So it's an interface standard. You can imagine once you have your software in one of Cortex-M core, let's say M4, and because the interface is standardized, so that core, you just don't need any modification ideally. Then you can migrate between different Cortex-M core could be M55, could be M85, could be M52 that I just mentioned. So that largely help you to reuse your software and also the software investment. So Synopsys, which is a set of API, software component tools, all those things, and basically standardize the software interface to the Cortex M. Yeah, next slide, please. So that is Synopsys software standard. Right now for the machine learning, of course, the API or software component, those can really help you. But not only that, how the software stack can really help you in the overall flow. Somebody called it continuous integration. I think that is also an important part because the machine learning model, you need to train that, you need to fine tune, you need to deploy that in your device. How the tool or software stack can really help you to construct the overall flow, that is actually important. So we categorize this by several stages. For example, the capture data. In Synopsys, we have standard, we call this synchronized data stream, basically the standard framework to handle the input data that easy your work. After you capture the data, then you can migrate to the data import. That is the standard label, standard data format file as well to like make it easier for our customer can import the data easily. And then, of course, you can go through your training flow to refine or to fine-tune your ML model, and you can deploy it to the target easy, as we mentioned here, TDK Kiso case. So Synopsys is not only, yes, there's many software component, API, it's an interface, standard interface, but it can also help you to go through the whole machine learning journey as well. Yeah, next slide, please. Finally, a couple slides. I think performance, even is just like running on an MCU device, but I think most people still care about its performance. So finally, just a couple slides show you what is the performance uplift. What you see for some common, I would say, benchmark that we here. That's said, for example, in this diagram, which is run in audio mark, normalized per megahertz to show you what is the performance improvement from all the way from the M4 to the M85. So it's scalable, and customer based on their need to choose, okay, where my MCU selection should land. In this audio mark, of course, we'll combine different score like a beamforming, noise suppressor, or some feature extraction, especially in speech, or some like new level type speech recognition. So over you can see, especially if you enable the Helium, you choose Helium enabled architecture, that really give you high performance into even just in the MCU space. Yeah, next slide, please. Right, this one is running another workload. Audio mark is a reference, but typically in more DSP type of application, I think people care about FFT or DCT because this is the fundamental calculation. So this also show you, like last slide, show you what is. But in this slide, differences is the lower the better because it shows in the y-axis it shows actually is the cycle count. So it's the lower, the better. So you can see goes to M52, M55, M85, it's just getting lower and lower. Yeah, next slide, please. So I put this in the last because it's the not that kind of performance related, but we also have like a software tool to help customer to arrange this machine learning work, because machine learning is not just one block. If you look into that application, it's just one after one after one. So with that, there should be like after you have your input signal, that you can think about how to handle that for your signal conditioning that the diagram show here. After you condition that signal, then of course you go through some feature extraction, neural network operation, and classifier all the way to the output your signal. So since the stream basically is the package to help you how to standardize this kind of flow control, or said like stream signaling control, so that to make your life or make developer life more easier. That is the CMC stream. Yeah, next slide, please. This is my summary. So key takeaway for everybody, we go through what is Helium. It's we bring SIMD technology, vector processing. It's a single instruction, multiple data onto the MCU. Before there could be different, I would say, implementation on MCU. If you want more performance, you may add other component. But now we integrate that SIMD into the MCU, so to really easy customer choice. And then we cover how to use that. There's CPU core. There is a platform offering. In the software, we have open source and also have standard software to help our customer. We also showcase OpenMV example, how to build in the vision library, and also the performance uplift in computer vision. And then we talk about ML, AI on the Cortex-M. We show you what is the performance will be on the DSP ML. And also we have our tool framework, we call it CMSys, to help our customer. Overall, yes, I will pause here and happy to hear if any question or anyone.
Great.
Yeah.
Thank you, Stephen. So is there any questions for Stephen from attendees? Great presentation. It summarized a lot of use cases especially for Edge AI. I think one of the most important challenges that people face when mapping application on edge devices is the software stack, how to quickly bring up a demonstrator and then refine it for commercial use. You're talking about one step, which is signal conditioning. Can you elaborate on that and how this is supported in the whole flow? Because signal conditioning is a very important step. If you don't have proper signal conditioning, you will have wrong results. So how you cover this step, and also if you can elaborate on how the flow adapt with the new algorithms. For example, in the AI space, the increasing complexity. Every day we see different algorithms. So how this architecture will deal with that?
Yeah. So with that, I encourage people to go to our developer.com. Keyword is MLEK, like machine learning evaluation kit. Those are like example that we collect to help customer quickly get into ML space. That will include the signal conditioning, like, or some people call it pre-processing that you just mentioned. So there is a video type signal, there also audio type signal, cover the speech, how you should be conditioning that, and also what is the related or available library there, so you can use open source.
Great. Any additional questions from the attendees? We still have a short panel session. If you have questions, you can ask them in the panel sessions. So let's welcome Hajar Abdi, radar and AI engineer at University of Waterloo, sharing insight on next generation AI resident activity monitoring. Hajar expertise in healthcare AI solution promised to revolutionize the elder care. Hajar, the stage is yours. I see your slides. You can start.
Hello, everyone. This is Hajar. I'm going to talk about next generation AI resident activity monitoring from University of Waterloo and from a local startup in Waterloo called Gold Central. So today in my talk, I'm going to talk about our resident monitoring using radar technologies. I also want to introduce digital twins to overcome a data shortage for training AI models. Also, I'm going to briefly talk about our in-cabin sensing application using AI. I'm going to start my talk by a quote from one of our seniors. Visited one of our open houses back in September. The quote was, wait, and wait. This is the most repeated word we hear every day. I think you also might have experience, especially if you go to hospital for emergency department, you have to be waiting. So the problem we think is extreme staffing and resource shortage issue, sometimes with tragic consequences. The solution that we have is AI-powered radar-based technologies that can act as 24/7 caregivers working around clock, detecting any abnormalities and identifying underlying issues or predicting signs of illness. Why radar and why not current technology? We have the most popular technology we have for activity recognition, fault detection, and resident monitoring is wearables, which are annoying, intrusive. People might not be willing to wear them. Stigma around that, like I'm old, and battery issues. Another solution is camera, which is the big no because of the privacy issue. Call bell and telehealth are the other technologies currently being used in long-term care facilities. Like you expect someone when fall down, reach the call port and push the button, which is kind of impossible. What if they have dementia? What if they are unconscious, nonverbal? These are all issues that can be solved by radar technologies, non-contact and non-visual based system. How radar works is we transmit electromagnetic waves, receive the reflected signals. Our AI and signal processing model analyze the reflected signal and interpret it to classify the type of activity and many other things. So assume you are in a pool. When you are in a pool, like real pool, when you jump, when you swim or stand in the water, the created wave is completely different. Same happens in here when we install our radar sensors in our home. We are in a pool of electromagnetic waves, and depending on type of activity we are doing, we receive different type of signals. We install the radar sensors, as you can see here. You can kind of think about it as a Wi-Fi router, but at different frequency range and much lower power. We install it on the wall, for example, in a washroom, living room, bedroom, wherever you want to have coverage and monitor your resident. And our AI model in the edge server side will analyze the data. One of the problem, not the problem actually, one of the needed or requirement we want to have is data for AI model. So because radar technology for in-home monitoring, for resident monitoring is kind of new technology, we need to collect our data by ourselves. So we ran data collection campaigns, different places with different people with different activities to train our AI models. So as you can see here, we have different people acting as our fall or different other activities. We collected the data. This is how radar results look like. Sorry. This is completely heat map. You can see here, this is range elevation, range azimuth, or range velocity or Doppler effect that you can get from the radar. We have to have a label for our data, and because we are not allowed to use camera in many places, we need to have order of activity based on like what we order our participants. So we have this label, we have the data as like heat map or signals, we train our model. Depending on the type of radar sensor you're using, you might be like applying some pre-processing like FFT, clutter removal, MTI. And this is a range Doppler or range azimuth heat map that is something that you can feed your AI model. This is the high level of our processing chain. Firstly, we want to know if the room is occupied by a resident or not. If it's occupied, then we have people counting based on AI, like to know how many people are in the room. If we have more than one people, then one person, then we have the required help needed for our residents. So we don't need to activate other algorithms. Whereas if we have only our resident, we will have parallel processing like activity recognition, fall detection, positioning, embed function for our platform. All of these are challenges, like how we're going to implement, how we can scale these sensor up. That, like, I think you had pretty nice presentations today regarding the platform to use AI, to implement AI. And the overview of our solution is we have the radar sensor working 24/7, continuously monitoring our resident. Our AI model analyzes the data, the current data for real-time status, the historical data to change any degradation to our residents' baseline, and also send alert to caregivers, physicians, whoever is responsible for resident. Again, this is like having a pool of electromagnetic wave. We install 3 sensors per room for long-term care facilities. Our AI model can recognize falls, send alert for bed movement detection. For example, we have residents with dementia. They have lost their ability to walk while they don't know. Immediately, for example, overnight, they want to get out of the bed and they will fall down. We detect their bed movement. We track any changes to their normal activity and send notification. This is how we implement our system. This is our radar collects data. We have Ethernet-based system, Ethernet-based platform. The data is streaming over Ethernet to our edge server in the facility. Edge server is processing our signal processing and AI models for the detection. The results will go to our cloud-based server, and we have monitoring platform, which is smartphone and web-based applications. So for training, CMC was played a great role for our training part here, and we use our train model in the edge server in long-term care facilities. We have different type of alerts. For example, if any fall happened, the notification will be sent to the closest caregiver. They need to respond it. If they are unable to respond, they have to push the button of unable to respond. That can be escalated to other closer people around. And if they respond, they need to confirm if it was fall or not. That helps us to improve our model over time based on each individual. We have other alerts as well, like bed exit, as I mentioned. They need also to confirm it. We have suspected out of bed. We have some residents, they get out of bed and they don't know how to get back to their bed, for example. Same for their room. They go out of their room and then they don't know how to get back. We also have prolonged immobility detection. Like we have some residents, they cannot reposition themselves. That can cause pressure ulcer and other problems that we detect that one too and send notification. These are like instant alert that needs immediate response. We also have another type of alert that we believe it saves time for our frontline caregivers, that we send notification only if we see changes in our residents' normal activities. For example, for toileting. If we see any changes in their toileting habit, for example, our resident went to washroom 4 times, the average was 4 times, and today he went 9 times. Something might be wrong. We don't know what exactly is wrong, but we know something might be wrong. Maybe it's because of they had too much liquid, but other maybe UTI problem, some other problem. Same for activity, like their active versus sedentary hours has changed. maybe if they're more sedentary today, maybe they're depressed, they are having like other issues like dementia or microstroke or other things. Gait analysis also is kind of our vital sign that we detect over time, and if we see changes, we send notification to caregivers. Otherwise, their data will be stored in our dashboard for physician or whoever is like analyzing their data over time. This is the like overall dashboard. As you can see here, we have n number of rooms in a facility. If you want to know what is like your resident doing, you can see it, the real-time status from the dashboard behind the closed door. And clicking on each room, you can have the like trendal activity over time, for example, like the active sedentary hours over time, day, months, or year, or for example, washroom, or even bed movement, bed exit routine as well. So this is our solution for long-term care facilities that we are installing our radar sensors in long-term care facilities in Waterloo now. So based on the like a completely AI platform servers. Another technology that we are using and working with HFSS is digital twins technology. So one of the requests we got from facilities was, okay, fine, you can detect fall, but like how severe a fall can be, how can you know this? Based on the information we have from the facility and also information we have from radar side, like position of the fall, either it's near bed or in washroom, in bathroom, or point of contact, which part of the body hit the ground first, or speed of fall, we can identify the severity of fall. Because for training our model, you need to have data for sure. And we needed to ask participants to come in and fall for us for 1,000 times, which almost is impossible, which is why we used digital twins, that we trained our model based on the data we got from ANSYS HFSS, and then we trained the model, we used the trained model in a real fall scenario. Or for example, this is another crazy scenario for fall that no one is going to mimic this fall in real life. Which is why we use digital twins. This is the accuracy, which was amazing based on the result we got from simulation data, for example, showing knee first, like fall based on knee hit the ground first, or hip hit the ground first, or full body. So the result of this study is kind of risk assessment fall detection that can show which part of the body hit the ground, where, and how severe it could be based on this. So as you can see here, if somebody hit the ground from head, it would be the most dangerous part that needs immediate attention. If our caregivers are busy with different things, they have to respond to this immediately. So this is our digital twin that helped us for fall severity detection. And also we used radar sensors for in-cabin sensing for other applications, like based on collaboration with several radar and automotive companies. We showed that radar can detect when a child or pet has been left behind the car. We can count how many passengers are inside the car, which seats are occupied, and the type of occupancy. If, like, for example, seat number 4 is occupied, what is the type of occupancy, if it's a kid or an adult, and same for distracted driver detection. So because it is electromagnetic waves, it can penetrate materials, which is one of the strongest part of the radar, in addition to privacy, that like even if our kid is under the seat, we have this reflected signal, as you can see here in your left. For like occupied seat counting and type of occupancy, we implemented our AI model in CMC Cloud for like counting, identification of passenger type, as you can see here, the accuracy we got was 95% for detection, 89% for counting, and 74% for classifying passengers. This is for in-cabin sensing based on radar technologies, and yeah, radar can be used for different type of application for like inside and outside cars and inside and outside rooms. Thank you so much. Thank you, CMC, and thank you, everyone. If you want to know more about our technologies, our solution here is our publication we have so far.
Thank you, Hajar. Very nice presentation and very nice use case of AI. We open the floor to questions. Maybe one question. So this is a startup. What is the main challenges you have faced to take this solution to market, especially on using the AI hardware accelerators? Can you summarize some of those?
Yeah, I would say the most challenge was how we can scale up our system. So we develop our algorithms on using one sensor, for example. All was like one sensor, and then we went to like, okay, 450 sensors for one facility. How you're gonna use your current algorithm, your current model, that you can use a system that is cost effective, it's not super expensive, and also fast, real time. It is in real time. Fall detection, you cannot detect the fall after 2 hours. You have to detect it immediately. It should be super fast. And yeah, these were all the issues we have been facing over the couple of years.
I also have a question from Flo. Which radar are you using? Is it something off the shelf, or you developed something specific?
Yeah, this is very good question. We use different type of radar. We use off-the-shelf radar, and also we developed our own, like we customized our own radar sensor.
Thank you, Hajar. We need to move to our next speaker. Thank you for your great presentation. I will introduce our next speaker. He's a long-term contributor to the workshop. And it's my pleasure to introduce Andreas Moshovos, professor at University of Toronto. He will delve into machine learning accelerators, offering invaluable insight into training and inference optimization. So get ready for a session packed with knowledge. Andreas, the stage is yours.
Okay. Now
I hope you are able to
share on my shoulders at the moment. So it's always a pleasure to participate in this, and thank you for.
Okay. We see your screen.
Right. Yes, like you. So thank you all. I appreciate you staying, even though it's been a long day. Let me get to it, and then we can have a discussion, I guess. So my point today is to summarize some of the what I find the more interesting work that we're doing in the group. This is not my own work. There's a lot of people involved over here. And let me start quickly in saying the following. What is our goal here? The goal is to make possible to run networks on devices that normally would not be able to support the type of compute and the type of memory the demands they have. So we're trying to reduce the cost of deploying models, and this can have benefits in terms of the uptime, the energy, the cost it takes you to run them. It can also mean that we allow more powerful models to run on specific devices that cannot run them otherwise, or to allow models that are more responsive, reduce the time it takes for that. Now, there are a lot of challenges in doing that, and it's a pleasure today to be in such a distinguished group with people that actually build devices. I'm actually envious that you get to do that, but there are some benefits of being a university. I understand that. So one of the key challenges is that your workload itself evolves quite a bit. I mean, people did mention AlexNet as the key inflection point for machine learning. Since then, there have been a lot of different networks, and if you dive deeply inside, you'll see what kind of layers they use, what's the sizes, how they're connected. All of this is changing, and who knows how things are going to evolve in the future. And yes, transformers are dominating at the moment, but there are other things that are equally important, like nerves, Gaussian plotting, what have you. There's always something new. So the question is, what can you do, first of all, as an academic, in an environment where you get to work with very bright people that are much more intelligent than you, but you are going to be working with them for 2 years, maybe if you're lucky, 5 years, and then they move to bigger and better things, right? And when we started working on that, we were thinking, what kind of devices will we build? But now, thanks to all of you, there's tons of them out there. So I'm thinking as an academic, if I go and promise you that somehow I'm going to come up with this wonderful new idea that's going to revolutionize the accelerator domain, I think this is a tall order. And my hat's off to people that are trying to do that, and I'll be very happy to hear that they succeed. What we think is one way to actually contribute in this ecosystem, instead of trying to say, throw everything else that you've done so far out and try to redesign something from scratch, can we come up with things that you cannot do these designs, either at the hardware level, hardware is always harder, or completely at the software level, that will make them behave better, right? And this is what we're focusing on. And as a group, we're focusing on something that we feel is an invariant, that no matter what type of network you're running, at the end, you're doing a lot of multiply accumulates. And our emphasis lately has been on trying to reduce the cost of transferring the data for this. We have a lot of other work. I'll be happy to talk to you about how we can reduce the computation as well. But today, I'm just going to focus on one thing. And coming from my prior life, I was focusing on general purpose processors, performance at all costs. And coming from that, we're trying to avoid asking programmers to make changes. All right. So today I'm going to focus on this thing only. And what is the key idea behind it? Something you know better than I do, that training is expensive, right? And everybody wants to train, but it takes forever, right? And actually this image was generated by a transformer, right? So our goal is to try to make training faster and to improve the energy efficiency of it. On top of that, as an added benefit, what I'm going to briefly touch upon today is a technique that actually reproduces a network that's also efficient for inference. What I'm going to present to you is not quantization. I would like to emphasize that, and I'll try to explain it better. So let's go quick overview so that you can all double check that I know what I'm talking about. What happens when we train things? We typically use gradient descent. There are many different solvers. There is a
Andreas, we lost you. You are muted.
I think I'm pressing the wrong buttons all the time. That's what I did. Sorry, I was just trying. You can hear me now, right? I'm guessing. Is that
Yes,
a yes?
we hear you. Yes.
Okay, and you can still see the slides, right?
Yes.
Wonderful. Sorry for this. So what I was saying is I'm going to do a quick overview of gradient descent, right? Very quickly. The goal with gradient descent is to try to learn a particular task. And how well you learn this task is solved by a loss function. I don't know if you can see my cursor. Can you see my cursor moving?
Yes.
Wonderful. All right. So we do a forward pass of the network then, right? Let me see. I'm actually clicking on the slide so you can see the slides. Okay, good. So we're doing a forward pass of the network. The network initially is random values. We calculate the loss, and then we do a backward pass, and we're saying, how should we change the weights so that we better the loss improves, right? And in order to do that, unfortunately, we have to save all the runtime calculated values from the forward pass and reuse them in the backward pass, all of them. And that takes gigabytes of data. Even for something as simple as ResNet 18, you're looking at 5 gigabytes of data. God help you for something more interesting than that. And, everybody knows that. And what industry has been doing is they were focusing on the fundamental problem. What kind of data types should I use to do the following? To be able to converge, that is, learn the task successfully, and at the same time, use as less data, store and transfer less data as possible to my memory. So, just an indication here, my apologies to other people who have done tons of work on that. If you follow the history of what has happened the past 10 years, people were training with FP32, then there was brain format 16, there's FP16, there's FP8, there's FP4, there are microscaling formats and anything like that. This is great. The question is, what can you use, right? So people first started using FP32, and just to make it clear, we're talking I have a chip, and unfortunately I have to go and store my data to some other chip, potentially in another node as well. People started with FP32, then they went to BF16, they went to FP8. There's a lot of work that goes into trying to converge with this. Maybe there's FP6, IBM has FP4, there's microscaling formats from a consortium of companies right now, but always there's a trade-off between accuracy and efficiency. You want to use the minimum possible data type, but at the same time, you want to converge. And what we have found is that if you do the selection well, you end up with a different data type per tensor. So this is supposed to be a mock diagram of a small network. There's a bunch of layers over here, and we're showing you as a diagram what happens to the data type that you would like to use if you care about maximizing your accuracy and at the same time minimizing your traffic and storage in memory, right? So unfortunately, presently the mode of operation for people is, look, we provide you the data types. Maybe we provide you a library that can help you train with a particular data type, but it's up to you to try and see if it works for you, right? So it's a trial and error process. So our goal, and with this project, was to automate the whole process. So we have produced two methods. One is less intrusive. The other uses the very training process we use for neural networks to tell you, you have a network with 100 layers, great. You have 200 tensors. You have to pick 200 different data type selections for those tensors. We are going to learn those tensors, and we're going to do it on the fly automatically for you. As an added benefit, we're going to make training faster, we're going to store less data, and you're going to get a network at the end that is actually faster to run inference on. So sorry, I'm running, so we stay up on time. So we have two key methods. One is a black box sampling approach. The one that I'm most excited about is the machine learning approach. And finally, on top of that, we do have a piece of software hardware you can add that further compresses the data when you put them in data. What I would like to emphasize is these techniques require no specialized hardware support. You tell us what data types your machine supports, we'll tell you which one to use for which tensor at what time. Just so that we understand what the problem is, typically training happens with floating point. Right? We have in floating point, there are three components in the data type. There's an exponent, there's a mantissa, and a sign. What our method learns the bit widths for those. What we do is when we compute with the baseline data type you selected, FP16, let's say. When we transfer data to memory, we just chop off a bunch of bits here. We make them zeros. When we bring them back in, we expand back to the data type you want. That's how we save time, by saving the traffic to memory. You can still use the same compute units. Now, and so that you get the sense of what this technique can produce, what you're looking here is a number of layers of ResNet 18. And along the y-axis is the number of bits that the method learns over time. I'm starting with the activations. This is the number of mantissa bits that you learn per layer. You notice there's not a single selection that is best. And if you were to pick, say, 8, you're taking a chance, and you may not actually converge because one of them uses 9. If you pick 9, there's a lot of opportunity you're losing because a lot of the layers don't need 9. This is just for the mantissas in the beginning. The next is the exponents. And then this is the sign with the sign bits. Then we go to the weights. And this is what happens over time when we do training. At the end, you do end up with a network that says, for this tensor, you need this data type. So this is a fairly complex problem for a human to do optimally, right? And the power of our method is that we can do this automatically for you for any kind of platform out there. So unfortunately, given the amount of time we have, I won't go to how we actually do that, but I'll be happy to talk to anyone that's interested in this. We plan to release this tool as an open source for non-commercial use, and we're probably going to try to do something commercially with it as well. So long story short, we do have two methods. One is a black box sampling approach. I'm going to briefly touch upon that right in the next slide. The next one is a machine learning approach that basically uses the very same training algorithm and asks us to also optimize the data type you're using during training and for inference as well. And then on top of that, we have an exponent compression. Very quickly, you pick one of the two as the first layer, right? This is the part that optimizes the data type itself. Optionally, if you wish, in software or in hardware, you do data compression on top of that. And we offer you also IP blocks if you want in hardware that you can incorporate into your design if you're doing hardware and you have that capability. I'll explain the simpler method, the one that is a black box approach. What this method does, it looks at the loss function as it progresses during training, and then it adjusts the mantissa and the exponent. It does several trials over different batches, And surprisingly, he manages to reduce both the mantissa and the exponent very well. This is by just observing the loss as it progresses. The other method I'm not presenting today, but I'm happy to talk about, he uses stochastic gradient itself to learn both the exponents and the mantissas. And it can be used also for learning integers for inference as well. Last thing I will touch is the compression method. When we learn the exponents, let's say you started with exponents that had, I don't know, 8 bits, and we learned that for this particular layer, you only need 6. In reality, when you do training, most of the exponents tend to cluster around 0. Right? Now, when you do that, however, what you have done is you're storing all the values using as many bits as necessary to store those very few values that actually need all those bits. There could be 1 or 2 values every so often that really need all those 6 bits you decide that you need. In reality, though, most of them don't need that. So we have either a software or a hardware component. The hardware is, of course, much more efficient, that when you send data to memory, it packs them using only as many bits as necessary, and it does it per group so that it's actually efficient hardware as well. Some data so that you know how well this works. These are the activations, the weights, and the total. This is for ResNet 18. As a proper academic, we have tons of data we can share with you for many different types of networks, including transformers. What you see is a breakdown of the bits used for depending on the data type you're using. This is FP32, BF16, and this is our best method, the one that uses machine learning. And I would like you to ignore the top part. This is the part that the hardware compression can remove as well. So as you can see, we can cut down the activations on average to less than 5 bits. That's when you do training, and at the end, when you for the weights is a bit more, right? And overall, we're looking around 6 bits on average for all the weights and activations across the whole network. But I will emphasize that the data type we choose is per tensor, and we can do it on a smaller granularity if needed. In terms of task performance, we maintain task performance within the limits you see. This is percentage. We have done some work on training, and if you do different training runs, you'll see there is a lot of there is variation across training runs. This is within the noise, and I'll be happy to talk about this more. This is how it really looks like if you scale it to 100%. This is the differences you see. Finally, and sorry for all the exclamation marks. These are my student's slides, and he's a bit more enthusiastic about things, but I think it's warranted. In terms of footprint, this is how much we reduce actually footprint in memory. And finally, so that you get something out of this in terms of the highlights, when we use the machine learning approach, we can cut down traffic to about 5.6, including the hardware compression. And when we do the trial and error, we can get 4.6. Right. We'll be happy to talk more about this. And thank you again for inviting me. And I'll stop here.
Thank you, Andreas. As usual, we learn a lot from your presentations. Is there any questions from the chat? What are your thoughts on the role of FPGAs for running this neural network model? Have you used them?
I use the FPGAs as well. We have some other work. I predominantly use FPGAs as a prototyping mechanism. I haven't used those. I know that some companies they are providing FPGAs on the cloud for themselves and for customers. I also know that some of them are shutting them down as well. So I think the jury is still out. The technology we have actually play very well with FPGAs, because all the stuff that I said was started first as a hardware project, and it has evolved into a software stack, because effectively I think hardware is going to get harder and harder to get into at this point. Right. So yes, I mean, this will be golden for FPGAs if you wish, because we can give you data types that don't actually exist on the hardware directly.
Great. Thank you, Andreas. We will move to our next speaker. It's Professor Warren Gross, a long-term contributor to Acceleration AI. It's our pleasure to welcome you to present today. And Warren will be presenting some insight on hardware for stochastic simulated annealing to solve large-scale combinatorial optimization problems. Warren, the stage is yours.
Okay, thank you very much. First of all, can you hear me?
Yes.
Yes. Okay, so now I'll share my screen.
Yes.
Okay, let me just see if I can make it full screen. How about now?
Great.
Great. Okay, so thank you very much, and I'd be happy to talk to you today about another style of AI algorithm and how it can be accelerated in hardware, and this is that of the solution to large-scale combinatorial optimization problems through simulated annealing. So AI compute is requiring lots and lots of hardware. As we've heard today, the theme of today was hardware and software for mapping large-scale, high-compute AI algorithms to hardware. And so there really are new technologies coming on board which are going to open up many different possibilities for AI. And so if we look at the technologies that are becoming apparent as Moore's law marches on. So there's, first of all, from the left to the right, the Moore axis, where we have higher and higher levels of integration, marching towards 1 nanometer technologies, and also higher degrees of integration into 3D. And as well, there's more technology progress in using beyond CMOS or other kinds of technologies such as photonic ICs or spintronics, or different kinds of integration. As well as the new devices that are coming online, there's also whole new computing paradigms to consider, such as quantum computing. So the combination of these new paradigms and new technologies will open up new opportunities for algorithms and applications that exploit the possibilities that these new compute structures will make possible. So one of these applications in AI is optimization, and optimization is used throughout a wide variety of different industries and different applications. Very useful in logistics, the algorithms that underlie VLSI design, wireless networks, robotics, finance, and drug discovery are just some of the applications that make use of advanced optimization algorithms. So an example of an optimization algorithm is applied to the traveling salesman problem. So this is a well-known problem. This is the problem, say, you have a salesman that wants to travel on a path of cities and find the shortest path, given a list of distances between pairs of cities, the shortest path that starts at a particular city, visits each city exactly one time, and returns back to the starting city. This, of course, has many practical applications, obviously in logistics and transportation, but other applications as well, such as network optimization. And so you can come up with a naive algorithm to solve this. It's pretty straightforward. You just you make a list and you start swapping pairs of cities and calculating the length of the path of this new path every time. And you simply choose the path with the lowest overall distance. The problem with this algorithm is that it's computationally intractable. There are just too many paths to consider. So this means we have to come up with better solutions. We cannot just do brute force optimization by listing all the possible solutions and choosing the best one. So to illustrate why that doesn't work, let's say you have 50 variables in your problem, and you want to find the best configuration of these 50 variables. Let's say they're binary, so it's the simplest possible problem you could come up with. Then there's 10 to the 15 possible configurations. If you have 1,000 binary variables, which is actually a very, very moderate problem size, not even that big, then there's 10 to the power of 301 configurations to search if you were doing it through brute force, and that there's more configurations possible than there are atoms in the universe. So this is simply intractable. So instead, what we come up with are meta-heuristic optimization approaches, which are human-guided approaches that help you search the space efficiently to hopefully quickly come to an approximation of the optimal solution. And one such meta-heuristic approach is simulated annealing, called so because it has some analogies to annealing the metals to come up with steel that is very strong. And the way you do that is you heat up the steel and you control its cooling in such a way as to force the atoms to arrive and configure themselves in a low energy state, in a stable state, and that's going to make a harder steel. And the key is how do you actually control this cooling schedule, and that's what I'll talk about next. So the simulated annealing algorithms are using inspiration from the thermodynamic cooling. This is a cartoon that shows the basic idea of simulated annealing is you have some search space. I'm going to try to find the global minimum of a cost function. The problem is if I do greedy search by choosing different, say, random configurations and calculating their costs, then I may end up in some local minimum. So the way I avoid doing that is every once in a while, when choosing a random solution, I actually choose one that has a higher cost, though it should be worse. And I do that with the hopes of climbing over the hill and falling into a valley that has a global minimum in it. And you can see that the cooling schedule is actually going to be such that the probability of accepting a worse solution has this thermodynamic type style equation. Okay, so the kinds of problems you could solve with with simulated annealing are some typical combinatorial optimization problems, such as the traveling salesman problem. There's another one called max cut, which is a graph problem, and another graph problem called graph isomorphism. There's actually a set of canonical optimization problems defined on graphs that, in fact, many real-world problems map onto this set. These are just some of them. And so if you can solve this set of problems efficiently, then you can go a long way towards solving many practical problems. And simulated annealing can be used for these kinds of solutions. So we're interested in hardware to do annealing and annealing-like algorithms. And so what kind of hardware could we possibly conceive of in the next, say, 10 years to solve these kinds of problems? Well, there are, of course, the conventional processors that we have now, CPUs and GPUs, and these will continue to be around in the next few years. There's, of course, also workload-specific processors, such as neural processors, or what I'll be discussing in this talk, which are some CMOS, special purpose annealing chips, or even some new technologies such as analog computing or oscillators, optical computing, spintronics. These technologies are also very useful in solving these kinds of highly parallel, computationally intensive problems. And as well, there's a lot of interest in using quantum processors to do annealing. And in particular, there are machines called quantum annealers, which are specialized in doing just this. And of course, you could also conceive of universal quantum computing to do this as well. So the goal of our work is to look towards scalable, universal optimization engines that exploit massive parallelism. So here's a couple of different examples of annealing hardware that exists. On the left is a CMOS solution that this was published last year at ISSCC. And it's able to solve 4 2,000 variable problems. And I say that these problems are fully connected. You'll see what that means in the next slide. That's actually very important. But we'll get to that in the next slide. And compared to a fairly state-of-the-art GPU, this kind of solution has 58 times the speed up and 1/500th the power consumption. So you can see there's a lot you can do by coming up with ASICs to do annealing. On the other hand, there's sort of this esoteric solution, this quantum annealing solution. Here's a machine that is available from a company called D-Wave. This is a quantum annealer. It's not a universal quantum computer. It just does annealing. And this one you see here has 5,000 qubits. The problem with quantum machines, other than the size and the power consumption, is that the way quantum technology works now, it's very difficult to come up with fully connected graphs. And so what you have to do is embed the annealing problem you want to work on into a sparser graph, which requires you to use several physical qubits, to realize a logical qubit. And this actually has a quite important restriction on the size of problems that can be solved. And so we're looking for alternatives in the near term anyway, until such point as quantum supremacy comes, which we don't know when that will be, if it arrives for this problem. Okay, so the way we're going to approach coming up with a universal hardware for solving annealing problems is through a mathematical model called the Ising model. And the Ising model is a fully connected graph. in some ways it looks very much like a neural network. And each of the nodes in this graph is a spin. A spin is a binary variable with a value +1 or -1. The spins are all connected to each other through a set of edges which have each have a weight on it. As well, there can be a bias associated with each spin. So the idea is going to be to find the optimal configuration of all these binary variables, all these binary spins that is going to represent the lowest energy state of this model. And the energy of this model is called the Hamiltonian, and there's the equation there. Basically, it's all the pairwise combinations of spin values times the weight that connects them, and you add to that the product of the spin values and their biases. So it looks very much like a neural kind of computation. And so we can use annealing to find this low energy state of this model. There's a way to map problems to these Ising models, and therefore if you could build an Ising machine, then you would have a universal optimizing solver. And so we use the concept of probabilistic bits to implement the spins. I won't go through the details, but the equation is here. You can see it's a kind of a messy thing with some transcendental functions, which is actually very similar to a neuron. So you'll see it when we show you the hardware, it's going to look very much like a neuron. Okay. So the solution that we're going to briefly look at today is using kind of computing called stochastic computing. It's a highly parallel and hardware efficient technique that we're going to develop a parallel annealing algorithm for. So classical simulator annealing is actually sequential, where each configuration is tested one after the other, and so now there's interest in these parallel annealing algorithms where spins can be changed, multiple spins in each iteration of the search, and this can be done through quantum technologies or through CMOS technologies, and I'll be showing you some CMOS solution next. But first, I'll briefly describe the style of the computing circuits that we're using to design this hardware. This is called stochastic computing. The idea is to compute using random sequences of bits. And it's a very natural kind of computing for this problem because you need a source of randomness to do annealing. The idea being here, the canonical example of stochastic computing is the AND gate, which can do multiplication as long as the inputs are random sequences of bits that represent some value between 0 and 1, and when you take their AND of them, you have a sequence which is representing the product of those two inputs. So it's an analog inspired digital computing technique. It has this nice property of progressive precision. It has very small circuits, and it can be slow unless you find the right applications to use it for. And I think annealing might be one of those. This is just a note to show that we can represent both positive numbers or negative numbers and positive numbers using this kind of sequence. And you'll see here the basic operations, the toolkit we have available to design with. We can do multiplication with single gates, either with an AND gate or an XNOR gate, if you're going to use this positive-negative notation. And as also, we have this really, really powerful paradigm of using a finite state machine to be able to generate complex functions, or I don't mean complex, I mean complicated functions such as TANH or ReLU or maximum functions. And if you can represent these as a finite state machine, then you can represent the finite state machine in hardware as a saturating up-down counter. So I'll show you how we take advantage of that next. So this is the basic inspiration for the circuit. It actually looks very much like a binary neuron from a binary neural network. If you're familiar with binary neural networks, with binary weights or binary activations, the way we would do the computation is from a first stage, which is binary, which is where we multiply weights with incoming values, and this is done with XNOR gates. And you can, in the binary world, binary neural network literature, you see this happening. In stochastic computing, you realize that's the way you implement a stochastic multiplier. And then the next step is we could do purely stochastic addition, but it turns out that actually has very poor precision and can result in very, very slow convergence. So what we've done is we've replaced it with just an integer adder. So we take all the outputs from the multiplication stage, we add them up. And in the neural network world, that's called pop count. But it's just sort of the same thing we do in stochastic computing. And then what we had to do is develop a new form of stochastic computing that deals with integers that result from this addition. So we've applied that and then come up with integer analogies for all of the operations that I showed you before. So this finite state machines, etc. And I'll skip this slide. So I'll go to this. These are the operations look like. The additions are just binary adders, but you're only having to build an adder wide enough to implement the largest integer in a particular stream. So now our stochastic streams are streams of integers, not just streams of bits. We can have corresponding finite state machines to do, in this case, we need to do the hyperbolic tangent function. And then multiplication are binary multipliers. Now, the whole purpose of stochastic computing really is to get rid of building the need to build binary multipliers because they're very complex. But there's a trick that can be used where if one of the two inputs to the multiplier is binary stream, so if you have one stream that is binary purely and one stream that is integer, then actually you can use a multiplexer to do the multiplication, which is just a bitwise AND. So this really simplifies things a lot. So this is what the resulting hardware looks like. This is for each of those spins has one of these spin circuits. We call them spin gates. And these are all working in parallel, trying to come up with the right value for each spin. So the weights come in from all the other connected spins, and they're multiplied with these multiplexers. Then we add everything up with an adder, and then this up-down counter with feedback is doing the tanh function, and this implements the computation that we need to have. That you can see here is implemented with this fairly straightforward circuit. Okay. So I'm coming up to my time. I think I'm almost done. So we built some test hardware. This is a hardware which is on the way towards where we want to go. This is for 800 spin problems, which is a moderate-sized problem. It's not huge, but it's still fairly significant in complexity. And we started off by building a sparsely connected hardware. So each spin in our model is not connected to every other spin. It's connected to 8 other spins. And so we built a stochastic computing circuit to work with this architecture. And you can see here the plot of the energy for a particular problem. It's called max cut with 800 spins. And you can see how it goes down until convergence. In terms of the speed of this compared to simulated annealing, well, it's actually significantly faster. So standard simulated annealing, you can see in this curve is blue, and then our variants of simulated annealing, our hardware versions, are the green and the red. There's 2 different variations. Now you can see that the one problem you might see here is that there's some oscillations happening. But there's been a recent work which has addressed how to smooth those out. So that's something that can be dealt with. But you can see that the convergence speed is significantly faster because it's a parallel algorithm. Just to compare it with some recent work, these are both works that are done on FPGAs. The one on the left, IPAPT, is another kind of parallel annealing technique called parallel temporate. It's a slightly different approach, but equivalent idea. And there are some differences between them. So the IPAPT is only working with ternary weights, so weights that are -1, 0, or +1, whereas weights in our in our circuit can go from -8 to 7. So we're using more weights. It's a harder problem, as well as we are having 8 connections per spin, whereas ITAPT has 4. So it's not exactly an apples to apples comparison. And you can see that actually we do end up using a significant amount more LUTs. But the number of flip-flops is actually about the same, if not a bit less. But in terms of the speed, I think the thing to notice is that we're over 2.5 times faster in annealing than the other computing work. And just finally, just to wrap up, we're looking at ways to improve this. And so there's an algorithm called Quantum Monte Carlo, which is actually not a quantum algorithm at all. It's simply taking many Ising models, stacking them in parallel, and then coupling the spins between them. And so it's almost a way of exploring different solutions in parallel and choosing the ones you want, and you have a schedule where you change the coupling coefficient. So you start off by having this system kind of moving around a lot, and then slowly you tightly couple them so that they all find the same, drive towards the same minimum. And the basic result there is that we can improve the time to solution about an order of magnitude on some fairly large 2,000 node graph optimization problems. So in conclusion, we've been working on hardware for parallel annealing to solve optimization problems. And while quantum annealing, which is being held out as an ultimate solution for this, does hold a lot of promise, we're looking at what we can do in the near medium term. Can we have quantum-inspired annealing engines that are based on Ising models? Just that's what the quantum annealers do, but can we build them now? So we introduced a parallel hardware-friendly annealer based on stochastic computing and implemented a proof of concept that shows fast convergence, 1 to 2 orders of magnitude convergence time improvement over simulated annealing. So thank you very much, and be glad to interact with you all.
Thank you, Warren. Great presentation. Maybe one question: what is your future research direction to take this approach to the next level? And also, what are the main challenges you faced in comparing with FPGA? Yeah.
Right. Yeah. So in terms of future directions, what we're working on actually a couple of things. We're working on improving improving the performance, the convergence performance of these algorithms through different kind of techniques. So one I kind of hinted at was by using multiple parallel models and coupling them, so you're coupling in different dimensions. The other thing that we're doing is trying to apply this to some new application domains, and so some of the work that we've recently done is on applying this actually in wireless communications. There are some problems in wireless that can be solved using optimization, and so coming up with good algorithms to solve them and then implementing them in hardware is the next big challenge we're working on.
Great. So since we are 10 minutes late of the schedule, and since this is the last presentation, let's jump into the panel session. So I will invite all the speakers to enable their video and audio so we can start the discussion. All right. So I would like to thank everybody to stay and to enjoy this workshop. We covered a lot of content. Now it's time to have a panel discussion. It's an open discussion, so I will encourage the attendees to interact with the speakers, ask the question. But I will kick it off with this slide. So this is a summary of the CMC infrastructure to enable research and development in the space of AI. So basically, our objective is to enable our users to effortlessly train, optimize, and deploy their ML model on edge devices. The slide I presented earlier. We have active partnerships with leading edge companies such as Untether, Tenstorrent, OpenHW Group. Also, we have a partnership with ARM. So basically, the question I'm going to ask to the speakers is as follows. It's a high-level question, so you can take it from your perspective. The way we're going to run this panel session, I'm going to give 1 minute to each speaker to give his perspectives on what do you see as the most important challenges and opportunities in accelerating AI from the cloud to the edge. So you can take it from your perspective. You can fine-tune these questions and share your insights. I will start with Andreas. You are the first in my list.
I am, huh? Okay, that's not fair. Didn't have enough time to think about it. No, I'm not quite sure I will answer the question the way you're asking it. First of all, it's wonderful that you're setting this infrastructure. I think there's been some efforts from other institutions as well. I know Yoshua Benzo has been pushing to create a national infrastructure for AI, so this is a wonderful initiative. I think the most important challenge right now is how, besides the hardware, which is closer to my heart and everything, how do we enable people to actually use these technologies, right? Because at the end, the innovations will come from the people that have a use for it, right? So I think there's a lot of emphasis that needs to go into making these things accessible in a way that people can develop models and can develop applications as well. So having that infrastructure is a major point forward. Sorry.
Great. Stephen, from ARM perspective, what do you see as the main challenges and opportunities, especially for deploying edge applications on low-power edge devices?
Our view, I think, it's more in use case. As last speaker also mentioned, I think technology eventually you need to find it useful to people's life. And of course, there is already some use case right now. You can see the LLM in the market now. But I think for this technology really to be beneficial to people's life, we obviously need more. And another challenge that we see, this probably not only for the age, is that memory bound concern, or somebody call it problem, because now you can see in LLM, yes, there's many LLM model. There is some even maybe smaller or tiny, but you can see when you run it, and you can easily hit that memory wall. To say from the memory bandwidth, you can kind of quickly predict how the model would perform. So with that, how to either quantize the model to the size you prefer, or to say how to maintain the accuracy, or to say how to compress your model down efficiently. I think those things kind of concern that we see when we think about deploying machine learning, not only edge AI, not only generative AI to the edge device. Yeah, couple of our view. Thanks.
Flo, your perspective from RISC-V ecosystem, what do you see the main challenges and opportunities, especially in adopting RISC-V as a main hardware starting point for developing not only AI hardware, but AI hardware and software for a particular startup, for example? So what's your take on that?
I think there is a lot of opportunity, and with RISC-V you can address this. I mean, the span from a cloud to edge is really big, and you have so many different ways to innovate this, and that's where I see the innovation with something very open like RISC-V. You can make something very high performance predicting the weather, but you also can go through some application like radar for elderly people like we hear today. And then there is a second point, which also Steve mentioned, it's the power consumption. So it really depends if you're having an always on power, if you're depending on solar, but you still want to do it. Like recently I came across an AI camera, and it was powered by a small solar module and still transmitting some kind of spatial data, which we also heard before in a talk. So I think that is a great opportunity if you have an open and completely flexible architecture, which also provides you really variety of choices. Like you have a fully open source industrial grade choice, like from the open hardware, you can still license. You could completely develop in-house, like some of us do, Tenstorrent, for example. So that is a great opportunity. There comes also some challenges, which goes especially to the software ecosystem. I think in AI, that challenge is, there is a challenge, but it's not too big because this AI accelerators at the moment are mostly closed source, so it's controlled and customers don't write detailed programs, or it's possible to solve like Tenstorrent, but also Untether AI have showed today with good software stacks who are helping to abstract it and put it on the RISC-V. So I don't see much challenges. I see much more opportunities.
Great. Tom.
I definitely see a lot of challenges. That's kind of my day to day. So challenge number one is, how do you program all this new hardware, right? Like if hardware is changing so drastically, so quickly, how do you know that in 5 years it's still going to be something that's supported, something that you don't have to build a new engineering team every time you launch a new product? And yeah, in particular for Edge, I've seen that in prior roles working with embedded devices that have a long lifespan, and making sure you have that that trust. That's really, really hard. In terms of opportunities, there's the other side of that, which is everything is changing, right? So you can place really dramatic bets on different exponentials. So we're seeing, the amount of compute density, bandwidth, all of these numbers are going up by crazy amounts every year. So it's really impressive, what we're going to see today, but also the next 2, 5, 10 years on what can you do with, 1,000 or 1,000,000 times the bandwidth we have today. So there's just so many opportunities.
It's a very fast-moving field indeed, and I think putting in place hardware and software that keep up with this fast-changing landscape of AI is very important to secure success. Pierre.
The answer is yes. All of the above. More seriously, the first thing that came to mind when you asked the question is bandwidth. We started our first small, application-specific AI engine in 2013, and we put 64 max. And our latest machine has 1,000,000 max, and so we've scaled by, 5 orders of magnitude in the compute. But guess what? We have the same LPDDR4 and or DDR5, or a couple of those, right, that we had back in 2013. So bandwidth has scaled, orders of magnitude less fast than compute requirements and compute utilization. So we do see some HBM and some, high end, but in general we see LPDDR5s at the most, and a couple of even, the Nvidia machine you saw in the presentation today. So that's the first thing. So everything around bandwidth, and that is everything. That is the memory architecture, of course, the network on chip. So all of the clever hardware tricks, hardware cleverness to keep data close to your processors, share data with all processors that share feature maps or share coefficients, multicast, broadcast, reuse, recomputation to avoid having to, sometimes recomputation is a lot cheaper than reading the data from 3 levels down in memory. So there's a lot of cleverness in the hardware, and then even more cleverness in the software. So for us, our single biggest investment in the last 11 years now is the software, is to make use of this clever architecture, and the complexity of the software is around the tiling, the data management, the data movement, keeping all those parallel resources busy. And that has huge impact on performance, resource utilization, huge impact on power, because as was pointed out, and I completely agree, most of the power is in data movement, reading from memories, moving between memories. And the computation itself, is 10, 20, 30%, depends on if you include DRAM power or not. So Software tools, as Tom just mentioned, is the biggest one. And then kind of underlying all this is the hard lessons we learned. We started with the 64 Mac and it did CNN, right? And we thought, well, we're done. Guess what? Then we had 10 years of disillusion about how much flexibility you need. And so every generation, we're in our 6th generation now, every generation went from an accelerator progressively. Now we call it a neural processing unit. So never bet against flexibility, never bet against you have the clever optimization that works for transformers this week or this month or even this year that's going to be really the differentiator. Suddenly it's some other new, it's already happening, right? We already see diversification beyond transformers. We think they'll be there, but new stuff is happening. So you really have to think of a generic programmable tensor, parallel tensor architecture. So flexibility is probably the single biggest common denominator across the 10 years we've been working, 10, 11 years, and more of it every generation. Maybe as we get a little bit of kind of, as we had in CNN, I think we'll see in transformers some opportunity for adapting the algorithm to the architecture. We can't always start with pure software algorithms that have been developed on a high-end multi-100-watt GPU, and that's the right thing for the right purpose. But at some point, when you want to go into the 5 to 10-watt, inference embedded space, at some point you need to adapt the algorithm to the architecture. Right now, most of what's published has really been published and validated on a high-end general-purpose GPU. And so things like network architecture search, which was a little bit trendy a few years ago, I still think is a need in the space to start with a very good algorithm and then being able to adapt it to a specific class of accelerators. And between a Tenstorrent and an Untether and RNPX6, they're very different fundamental architectures. Some common elements, of course, but mostly different. And so we all need to have a way to take that really good win and make it a little bit better on our architecture. So I think that's a cost you have to pay to get the best utilization of your resources. And I'll be tempted to jump into controversy and say what's not the most important challenge is RISC-V. And I say that the Synopsys now has a RISC-V offer, so we have an ARC-V. So it's not that I'm biased against RISC-V. On the contrary, we love RISC-V. We've invested massively into it. We've announced that 6 months ago, so many of you are aware, and some of you are hearing it tonight. But so we love RISC-V for what it is, and it's a great approach. But we have, of course, in our accelerators, we've had previously standard ARC cores, and of course we're moving towards our RISC-V cores as controllers. Then the question is, and so they're great for that, and I saw that in the in the Untether. That's kind of for me the typical use case. It's fairly general purpose RISC-V that is controlling what are the hard to design network on chips, memory architecture, and what you guys call your PEs. We have our generic tensor accelerator and our convolution accelerator. Those are not RISC-V. They didn't start as a RISC-V or as any ARC core. They really start. We started a long time ago with that, but we found quickly, for us at least, we've invested more in very programmable, flexible, but very optimized processors, and we didn't find. Yes, there's a RISC-V in there, or there's a RISC core in there. Of course, there's many of them, in fact, but they're just controlling, and the hard part is all the movement of data and the special purpose super wide VLIW machines that don't look like don't start as a RISC-V and are certainly not a regular vector machine. So that's my kind of more controversial take on what is the key challenge. I love RISC-V. We use it everywhere when it makes sense, but personally, I don't feel that's the most important part of building a competitive, neural processing unit.
I like to see some controversy, especially in the 5th edition of Accelerating AI. This is why we are here. This is why we are organizing this panel session. I know that researchers love working with RISC-V because they have access to the RTL and they can publish research, and also for startups to start with something that is free and open source. I think there should be a lot of improvement, and to take it to the market is something that people should work on. But I like this these different views. This is how we can innovate and go forward. Jonathan, what is your take on that?
I really like the fact that programmability and usability came up so quickly, especially in the face of different use cases and rapidly evolving methods and research. And maybe the only thing I really want to focus on or add to that is you really, for this to be useful, it really needs to be applicable, programmable, usable all the way down the stack, all the way along this training, optimization, inference stack, so that people can do cool things. And you need to close this loop too, right? It needs to also go from inference to optimization as training. As people are, are starting to think about deploying really innovative use cases like this radar-based monitoring of vulnerable patients that we just heard about. You can't just, if I wanted to have a little mobile device that segmented images, could just pick off a good base image, good base model to start using. But for these new use cases, you need to train on your own data, need to optimize that inference, and then as you're gathering tons of data as you're actually using this, and you very reasonably, often many times more than you're going to be able to train on. So you want to be able to feed all that learning back. And so, I think for this to have the most impact, really need to have a coherent, stack that people can take advantage of all the way from build, optimize to deploy, and back again.
Thank you, Bill.
So I'll try to add something to what people have said, because I think I agree with 90% of what everyone's already said. But what I find interesting, and this will be coming from a hardware company, I do agree the software is probably the most challenging thing because the hardware is less important. But what is interesting is you can quickly tell who's actually monetizing the technology, who's actually building a product. You have so many people who are out there doing experiments and learning and figuring it out. And maybe they're using a particular model, but what they do is customize that model. And that constant customization is what makes it really hard to monetize. And I think somebody else said this earlier too, and I 100% agree, especially when you get into the large language model. Good enough is good enough, right? Do you need to have the best model possible, or do I need the best software possible leveraging that model? So I actually put more emphasis on the software, the application software, the software, because otherwise your edge device requires a cloud or a data center or the fog. And that's just not scalable, especially if you try to do real-time edge inferencing. And so from my perspective, I do find it that, I don't want to say an open source or commonality between the models, but some form of handling the flexibility of somebody feeling like they've tailored or customized the model to them, when in reality it's the software using it that I think matters more. So I'll end on that.
Let's go to Hajar. From your perspective, startup coming off of a research lab, I am sure you faced a lot of challenges. Can you share some of those with us today?
Yeah, I would say I'm happy with this question, and almost I would say 99% of what other people mentioned, I agree with them. We are using edge computing, I would say. We are not using cloud, so I would agree with edge computing for sure. We had lots of issues with cloud, like how much data we produce. We have tons of sensors. We have tons of, huge amount of data per second. We have to transfer it. We have to have very high speed bandwidth internet that we don't. So, which was our first reason why we used edge computing. This was first reason and first big reason. And then we are real time application, right? We want to detect fall and send alert immediately, or other bad exit. every second matters for us. If we don't have internet access for cloud to send this, to process this, then we should not be able to send anything, right? So that's why I think edge computing is super, super important. This is more like the opportunity side, but the other side, as like you guys mentioned, we don't have any optimized device that I can go get it and use it for my model. Like we are a startup, like we are developing something else, we are developing the technology, and at the same time we have to be concerned about like, okay, what is the proper edge server that I should buy for my that can handle all my sensors without adding too much cost for our startup. So these are all like the ideal word that for me as someone who is working at the startup for like long-term care, that would be someone has this edge server, I can get it and run it without being concerned like how can I optimize it, how can I use it, lots of things that I think can be improved.
Thank you. I think this is a common problem that startups face, is to what is the best platform should I use to get my solution to market. They have the AI skills, they have the algorithms, they have the data, they have everything, but the time to market is too long, and we need to create a resilient ecosystem in Canada, helping startups like yours accessing the best technologies through partnerships with companies, and help them get to market as soon as possible, because this is key to success. Last but not least, Warren, what is your take on the question? And I think you have some perspective from accessing high performance resources to conduct research.
Yes. So the disadvantage of going last is that it's all been said. So I agree with everybody that the problem, I think, is challenge really in software. And so the perspective I have there is, the game of edge computing has changed recently. A few years ago, we were playing around a lot with network architecture search and trying to grow models that on the edge that were coming from data you'd collect from your local environment. And while you're still doing that, really the challenge now is you have foundation models, and it's not just language models coming online, but many different, say a foundation model for every different domain is going to come. And how do you then integrate your data with the foundation model and do it in a way that makes sense, doesn't require too much compute, because we're doing this for every edge application. We can't train the new foundation model every time, and doing this in a way that makes sense for the hardware platform. So I think that's, I don't want to repeat what else said, but I think it's integrating foundation models into our edge cases is going to be an opportunity for sure, but also a challenge.
I would like to open the floor to the attendees. You can unmute your mic and ask questions, or you can ask questions in the chat. But I would also like to look back to Andreas to see if he has any feedback on all what have been said in this panel, because you've been first to answer.
No, I don't wish to take any more. I'll be happy to discuss, and I appreciate the spotlight, but I don't want to take too much of your time. I think CMC has played a critical role in fostering an ecosystem. In Canada, we're very lucky to have all this activity, especially on the hardware domain. Right, and I hope this continues like that. And if I start talking, I'll start talking about funding and government and what they're thinking. So maybe I should shut up, right? That's okay.
This is also important to enable research. I think there's a lot of there's tremendous talent in Canada, but the problem is how to enable research, efficient research. There's also a gap in HQP. So there's a lot of innovation in software, but not too much on the hardware side. And I think these gaps need to be bridged by initiatives and supporting for research. I have a hands up. Idir Milal, you can unmute yourself and ask questions. We have a couple of minutes, then we will conclude the workshop. So I think he's not able to unmute himself. You can ask questions in the... Yep.
Hello.
Yeah. Go ahead.
Okay. Thank you for speakers. Thank you for CMC. So I have a question related to hardware and software implementation and design. So every time when I did my design, so I don't know if we're going towards like high performance, more flexibility, or low cost, high cost, ASIP or ASIC. So I don't know what's your recommendation and how can we implement like when we have a very complex and large model. Thank you.
Anyone take this question?
I'll be happy to if nobody else speaks, right? I mean, the history of computing has always been about building machines for particular purposes, right? CPUs have dominated the field for decades, but even then there were microcontrollers, there were specialized accelerators. So I think there has to be an ecosystem, right? You have IoT devices, tiny CPUs that are very close to your sensors. Like you do have such an application spoken about today, right? And then you have the big data centers with supercomputers. So I think we need all of them. I mean, there's no question about that. And they're different bits, it's one of them. And a lot of work goes into them despite the computing powers.
Yeah, and maybe I'll add to that too. I mean, so for a good part of my career, I worked with FPGAs. And FPGAs were always the glue in the industry that kind of filled the gaps between what technology to the next technology, or pre-ASIC. People would prototype on an FPGA. I think the difficulty is that, and you could probably go back 30 plus years where, even processors have gotten heterogeneous, right? They're more complex, and it really comes down, I think, in my view, to system design. But those systems are now systems of systems. And so how do I distribute that system to do my compute in a efficient way? Not only power, but size and space. So I think that some people, if the volume dictates it, like automotive market's a great example, will build their own ASIC. They'll build their own SoC device. Others where, there's a lot of money to be had, like government, military, sure, they can still do it, but reality, they don't want to do those kinds of things. So I think it's very difficult because every market and even sometimes every application can be slightly different in what they need and want. But I think there's an overarching idea of system of systems, distributed computing, and using the different pieces of hardware to accelerate different components.
It's 5 o'clock. I think it's time to conclude the workshop.
So I'm going to just agree with Bill. You get the last word.
Yeah, I win.
Yeah, you won.
So thank you to everyone for joining us today. It's been an insightful journey discussing the latest trends in AI hardware, software, and application. A special thanks to our speakers and attendees for their valuable contributions, and let's continue to collaborate and drive innovation in AI together. So remember, the event recording will be available on CMC YouTube channel. So keep pushing the boundaries of AI. Thank you very much and have a nice day.
Thank you, Yassine.
Thank you, everyone.
Thank you.
Nice to
Bye-bye.
meet you all. Bye-bye.
Thank
Thanks,
you.
everyone.
Bye-bye.
Bye.